some nights, the sky feels loud with stories, but tonight it asks for patience, far from the comfort of easy stargazing. A faint traveller named Three-Eye Atlas crosses the inner system on a path that keeps slipping into sunlight. It is an interstellar guest, and we meet it at an awkward angle, where glare and geometry work against us. That is part of the mystery and part of the lesson. Objects are hardest to study when the sun turns them into a smear of brightness. Even a cooperative comet can vanish when the contrast is wrong. I find that humbling. Curiosity wants answers now. Observation sets the pace. We will take the long way around. We will separate what is known from what is guessed, and keep both wonder and caution in the same frame. You will hear Three-Eye Atlas compared with earlier visitors like Oumuamua and Borisov, but we will resist the urge to force a single storyline. Instead, we will build a ground truth, step by step, and let the evidence lead. If we are careful, the quiet details will add up. If this kind of quiet wonder speaks to you, subscribe and turn on notifications. The sky will do the rest. Before we chase possibilities, we owe ourselves a simple inventory of what is known about Three-Eye Atlas without decorating it with wishful thinking. In astronomy, that inventory begins with motion. An object that comes in fast enough to ignore the sun's long embrace and then leaves again on a forever path is not a local. Its trajectory is open, not closed. In plain language, it is moving too quickly to be captured for the long term by solar gravity alone. That is the first and most stubborn fact about Three-Eye Atlas. It is a visitor from elsewhere. The next reliable piece is direction. Most worlds in our neighborhood march around the sun in the same prograde flow, like cars tracing the same lane around a roundabout. Three-Eye Atlas approaches on a retrograde path, cutting against the traffic. That choice of lane is not a personality trait. It is a description of geometry. Retrograde does not make a comet unnatural. It makes it unusual, and it changes how, when, and from where we can see it. It also changes the speed of the encounters it has with the winds and fields that fill the inner solar system. Meeting the headwind rather than riding with it tends to sharpen interactions and compress observing opportunities. Once motion and direction are in hand, the third anchor is timing. The calendar matters because our instruments and our planet have habits and limits. The Mars encounter comes first, in the early days of October. Distance in space is always a compromise between enormous and intimate, but for scientists who pass near Mars is a meaningful chance. It means cameras orbiting another world may watch Three-Eye Atlas from a vantage point we do not have on Earth. After that, late October brings the curve around the sun. The curve is not remarkable by itself. Many comets turn the corner each year. What complicates this one is the alignment of Earth on the far side of the sun during the most revealing part of the story. The glare is not a metaphor. It is physics. When an object huddles close to our star from our point of view, the blanketing light suppresses contrast. Telescopes that would normally turn a faint traveller into data become nearly blind. Months later, in March, when the geometry opens again, Three-Eye Atlas will be farther out and fainter, passing beyond Jupiter's orbit, while we try to make up for lost time. That is the bare outline. Visitor status, retrograde entry, a Mars window in early October, a near solar pass in late October while we sit in the worst theatre seats, a later opportunity when it sweeps the neighborhood of Jupiter in March. The outline is not a mystery novel. It is a schedule. For professionals, it dictates proposals, target lists, exposure times, thermal limits, tracking rates, and 100 small decisions that turn night sky into numbers. For the rest of us, it tells a simpler truth. Our clearest view of this object will not be when we most want it. We will do our best work at the edges, before and after the sun has its say. In a documentary like this, it is tempting to race ahead and argue motives for the sky, but good work begins with constraints. What does it mean to know the path of Three-Eye Atlas? It means we have measured positions on the sky across many nights and fit a curve that predicts the next positions within known uncertainties. Those uncertainties are real. They shrink with more data and more baselines. They grow when the object fades, when the background is crowded, or when the seeing turns a star into a smudge. Astrometry is a careful craft. Underneath every confident diagram, there are columns of residuals, each one a quiet reminder that nature tolerates no shortcuts. What about composition? When people hear the word interstellar, they ask, what is inside? That question points to a different kind of measurement. Spectra are how we learn what a distant object is made of without touching it. You break light into its ingredients, and you look for signatures. Some signatures are loud and familiar. Others are faint and ambiguous. In the case of a cometary body, the distinction between the solid nucleus and the envelope of gas and dust around it matters. We do not measure the rock or ice directly. We measure the sunlight they reflect and the light that excites atoms and molecules and throws back at us, filtered by distance and geometry and the sensitivity of our instruments. It is fair to say 3I Atlas shows signs consistent with carbon-bearing material and ices that behave as sunlight warms them. It is also fair to say that declaring complex molecules with certainty from afar demands caution. If we want to stay on the side of truth, we keep our language disciplined. We talk about evidence consistent with organic material, not trophy words that outrun the data. There is another honest limit that belongs in the inventory. Rotation is how a small body reveals its shape and surface in the play of brightness over time. Many objects flicker with a rhythm that betrays their spin. For 3I Atlas, the rhythm is not yet firm. That could be because the coma blurs the signal, or because the nucleus rotates slowly or irregularly. It could also be a purely practical effect. Brightness changes that are tiny and smooth can hide in noise when an object is distant and faint. Here is the educational note I wish more of us kept on the desk. The absence of a clear rotation signal does not mean an absence of rotation. It means our tools have not yet caught it. Now a word about comparing visitors, because it will happen whether we invite it or not. Oumuamua was small by most measures and left quickly. Borisov looked like many comets we have known, a reassurance that not every interstellar object must be an outlier. 3I Atlas is its own case. Its envelope of activity appears earlier and extends farther than some expected. That observation says something about the surface and about the environment through which it is traveling. It also says something about how selection works. We find the things we are equipped to find. Slow, dim travelers can pass without fanfare. Loud ones with big envelopes announce themselves even to systems not designed to catch them. I find that reminder useful. Astronomy is not a neutral sampler of the sky. It is a partnership between what is out there and what we have built to notice it. Why is observing an interstellar visitor technically hard? Speed is part of it. Even when a body looks still to your eyes, it is moving across the sky at a rate that pushes tracking systems to be nimble. Faintness is another part. Time on great telescopes is precious. You cannot integrate forever. You divide the night among many priorities and take what you can get. Geometry is the third pillar. Phase angle, elongation from the sun, and the object's path against the Milky Way's crowded fields can each conspire to make clean data expensive. Add the sun's glare near perihelion, and you have a plan that must bend to circumstances. None of this is theatrical. It is why serious campaigns stretch across observatories and wavelengths and continents. If you missed one window, you hope a partner at another latitude catches the same scene from a better angle. If the ground is blind, you hope something in space is looking at the right time. There is a quiet education hidden in these practicalities. It is the difference between hoping to get lucky and designing a strategy that works even when you are not. Interstellar objects reward discipline. You write your questions down in advance. You decide which answers would be meaningful and which would be merely decorative. You choose the measurements that are most resilient to noise and bias, and you pre-commit to what would change your mind. That last piece matters more than we admit. In the age of instant commentary, the ability to adjust a belief when new numbers arrive is a form of professionalism. It is also a kindness we extend to ourselves. The universe is large. It will make liars of us all if we speak too quickly. Let me share a personal stance, because it colors how I read the sky. I think the most interesting posture is to be skeptical of our favorite stories and generous with the data that contradicts them. I like wonder, but I do not like being fooled. When 3i Atlas behaves in ways that unsettle expectations, I want to see those behaviors measured twice and interpreted slowly. If a natural explanation can account for them, I want that case made with the same energy people spend on extraordinary claims. If it cannot, then extraordinary work begins. Either way, the reward is the same. We learn what is actually there instead of what flatters our hopes. It is also worth noting what we do not need to decide tonight. We do not need to declare intent for a rock and ice body whose motion we can predict with ordinary gravity. We do not need to settle design arguments that are really arguments about human fear and pride. Those conversations have their place, and we will visit them later, but a good foundation keeps them from swallowing the whole house. What we need now is to accept the observing calendar as it is, to make the most of the Mars side view, to be patient through the solar glare, and to be ready when December brings the traveler back into darker skies. When that darker stage arrives, the questions will sharpen. How bright is 3i Atlas when the coma thins in cooler sunlight? Does the shape of the tail and the way it peels in the solar wind tell us about the sizes of grains and the energies of the ions that sweep them? Do the colors shift with time in a way that suggests changes in which ices rule the surface? None of those questions requires a leap beyond what comets already teach us. And yet, because this one comes from beyond the familiar reservoirs, every answer stretches models that were tuned to a single star's family history. If you like puzzles, you will like this stage. It feels like rinsing a fossil after the mud has hardened and the shape begins to emerge. One last piece belongs in any honest list of knowns. The size of the solid heart remains uncertain. Coma light, even when faint, can masquerade as a larger body. Phase effects can turn a modest nucleus into an impressive apparent magnitude. Your eyes want a single number. The sky prefers ranges and caveats. For 3i Atlas, the conservative way to talk is to keep to an upper limit in the realm of a few kilometers and a lower bound that remains open until better constraints arrive. Those better constraints do not fall from the air. They come from careful modeling that subtracts the coma's contribution and from observations taken when the geometry is kind. That means patient, repeated measurements with an appetite for error bars. It is not glamorous. It is how good answers are made. Comparisons with earlier interstellar guests are helpful when they remind us where the map ends. Oumuamua taught humility about shapes and accelerations in the small body limit. Bariso expressed relief that some visitors behave as the textbooks promised. 3i Atlas will teach whatever it teaches, but it will do so on its own schedule. The universe rarely repeats its lessons in the same order. If you have listened this far, you may be feeling the tug between wanting certainty and accepting process. I feel it too. I think the best way to honor that tension is to make peace with the inventory we have and to refuse to sell more than it is worth. The knowns are not nothing. They are clean, and they point us toward opportunities that will not return for a long time. The unknowns are not failures. They are invitations. They will shape our next questions and our next nights. Before we dive into debates about meanings and motives, we need to face a quieter challenge that sits at the heart of many misunderstandings. When you look at 3i Atlas, most of what you see is not the solid body at its core, but the halo it builds from sunlight and escape. That halo can turn a small thing into a big impression. To understand what the traveler truly is, we have to learn how to see past its own brightness. If the last chapter drew a clean outline around motion and timing, this one asks a harder question that seems simple on its face. How big is 3i Atlas? The sky rarely answers that directly. When a comet wakes up, it builds a halo of dust and gas called a coma. The coma turns a compact object into a soft lantern. Your eye, and even a professional detector attempted to treat a lantern and a lamp as the same thing. They are not. Most of what we see is the cloud, not the core. Separate the two, and size becomes an exercise in patience, not an act of looking. Brightness is our first seduction. A comet can appear generous with light, even when its solid heart is modest. That happens because thousands of tiny grains and molecules scatter sunlight in all directions. The camera records the sum of their reflections and emissions, not a neat silhouette of the nucleus. When we publish a magnitude, that number folds together many contributors. The nucleus reflects, the dust reflects and glows. Certain gases fluoresce when the sun pumps energy into their electrons. Point spread, the way optics and the atmosphere blur sharp points, spreads that glow even farther. All of it together can mimic a larger body. The coma is not lying to us. It is simply not the same thing as the rock and ice we want to weigh. Geometry tilts the scales again. At some angles, the dust acts like a finely ground mirror pointed in the right direction. When the sun, the comet, and the observer line up so that the dust is forward scattering, the coma brightens more than you would expect from distance alone. Near other angles, the same dust seems shy. The phase of the object, the slice of illumination that we see from our viewpoint, changes how generous the coma looks. A photographer knows this instinctively. Sidelight reveals texture. Backlight makes edges glow. Astronomy has the same tricks, only the stage is much bigger, and the lighting crew is the sun. There is a way to talk about intrinsic brightness that tries to cancel these illusions. We measure how bright the object appears at different distances and angles, and we solve for what the brightness would be at a standard distance and a standard phase. That exercise yields an absolute brightness, a useful but imperfect stand-in or size. It helps, but it remains a model stamped on untidy reality. If the coma varies with time, if the dust grains change size distribution, if the gas production rises and falls with rotating vents or fresh fractures, then the tidy correction in our notebooks falls behind what the sky is actually doing. This is not a failure. It is a reminder that the numbers we love are only as solid as the assumptions beneath them. So how do we approach 3i Atlas with the necessary humility? One answer is to shrink the measurement down to the tightest circle around the center that our instruments can resolve, then correct for the blurring that smears light outward. This inner aperture tries to capture a larger fraction of the nucleus and a smaller fraction of the coma. On excellent nights from excellent telescopes, it is good practice. But even then, the inner coma contributes meaningfully. Gas jets erupt from small areas, dig into sunlight like tiny fire hoses, and drag dust with them. The result is that the region right around the nucleus is not a clean window. It is a bright and busy neighborhood. Rotation adds another layer of difficulty and insight. Many small bodies betray their spin with a periodic rise and fall in brightness. Imagine a potato turning under a lamp. The wide face throws more light, the narrow side less, and the pattern repeats. On a bare asteroid, that rhythm can be crisp. On an active the rhythm blurs as the coma softens the contrast. If 3i Atlas spins slowly, or if it spins in a complicated way that redistributes activity rather than presenting neat sides, the light curve becomes subtle. Subtle is not the same as absent. It means we need more time and more careful filtering to see the beat. The spin matters because it hints at shape and internal strength. A very elongated body turning quickly would have trouble staying in one piece if it were weak. A more compact body can tolerate more. Gentle torques from sunlight or from jets of gas can gradually change the spin state over weeks or months. On some we have watched rotation periods drift as outgassing gently twists the nucleus. If 3i Atlas experiences similar torques during its warmer weeks, what we measure in early observations may not hold later. That mutability is part of the story. The nucleus is not a static stone. It is a working surface responding to heat, venting, and the push of its own exhaust. One of the quiet educational truths that comets teach is the difference between apparent and intrinsic. Apparent is what the detector sees, dressed in geometry and weather and instrumentation. Intrinsic is what the object would be if we could strip all of that away. The job of a good observing plan is to turn apparent into intrinsic, with as few unjustified steps as possible. That is why observers value multiple wavelengths, long baselines, and different instruments. A jet that is invisible in one color may stand out in another. A pattern drowned in noise on one night may resolve into a curve when you combine 10 nights taken from different latitudes. There is a reason collaboration is the standard, not the exception, on campaigns like this. When the coma is active and filled with structures, the inner pattern can betray the spin even when the overall brightness does not. Sometimes fans or spirals or corkscrew shapes reveal a repeating geometry tied to the nucleus rotation. On close, high-resolution images of well-observed comets, those patterns move with a tempo that gives the spin. For a distant, fast traveler like 3i Atlas, we should be cautious about promising that level of certainty, but we can keep the methods in mind as goals. If ground-based instruments cannot resolve them, perhaps a spacecraft looking from a different vantage, or a lucky night of exceptional seeing, will bite enough contrast out of the glare to show a repeating feature. Hope is not a method, but it is allowed to live alongside method as long as we do not confuse the two. The coma also fools our instincts about mass. A generous fog looks heavy. In truth, the cloud can be optically fat and physically thin. A little dust goes a long way when each grain is efficient at scattering light. The nucleus can sacrifice only a small layer of material and still present a broad face of brightness. This is one reason size claims based solely on how grand a comet looks must be treated with care. A strong source of gas at a few vents can drag dust out energetically, fake a big body, and then quiet down without drawing attention to the gap between appearance and inventory. With 3i Atlas, the most honest phrasing keeps to ranges and upper limits. A few kilometers as a conservative ceiling and room below that ceiling for the truth to settle is more defensible than any single number that cleans away the doubt. Jets and vents matter for another reason. They focus power into narrow regions of the surface, and that focus can act like an artist's brush, drawing asymmetries into the coma. To an observer who expects a neat, round halo, those asymmetries can look like a sign that the nucleus itself is lopsided. Sometimes that is true. Often, it is merely the signature of activity. As the nucleus turns, a vent that faced away from us yesterday may face us tonight, and the coma shape will shift to match. If you sample the comet only once, you cannot tell structure from choreography. Sample it over time, and the repeated strokes give away the dancer under the costume. Here is where my own judgment leans conservative. I prefer to live with uncertainty about the size and spin of 3i Atlas, rather than pay for false precision with confidence I have not earned. I have seen, more than once, how a number that comes too early ends up baked into headlines and expectations, and then observers spend months trying to clean that stain from the discussion. The better way takes more air into the lungs. You tell your audience that the nucleus is hidden behind its own light. You tell them that time and angle will improve the view. You tell them that when the phase is kinder and the coma thins, the corrections will sharpen. That is not hedging. That is fieldcraft. There is also a simple human reason to be careful. Stories about visitors from beyond our system arrive carrying big emotions. We are tempted to meet big emotions with big claims. But the strongest emotional payoff in this topic will always be the quiet moment when a new curve on a plot cuts down the uncertainty and pushes a blurry range into focus. The big moment belongs to the unglamorous practice of calibration, to nights when you reject bad frames, to the late correction that fixes a mistake no one else saw. I think that is worth saying out loud. The romance of astronomy is real, but it rests on the discipline of small, true steps. Because 3i Atlas moves against the usual traffic, its relative speed across the sky will change quickly. That speed affects exposure times and the shapes of stars in our frames. Track the comet too slowly and it smears into a streak. Track it perfectly and the background stars smear instead. That trade makes subtraction harder. It is not a flaw in the instruments. It is a geometric reality that adds friction to the seemingly simple task of measuring brightness. Add moonlight, thin cloud, and a horizon that eats the low-altitude target, and you begin to see why clean light curves are precious. Each one represents a night where many small things went right. When the object swings nearer the sun from our perspective, the dust can brighten from forward scattering, and the gas lines can change with temperature and distance. Both effects complicate the job of separating size from activity. On some comets, a dramatic brightening at extreme angles is more about geometry than about a surge in mass loss. Old photographs near the sun exaggerate scale for this reason. With three-eyed Atlas, we expect some of the same stagecraft. We should neither panic at a sudden blossom nor dismiss it as purely an optical trick. The responsible posture is to ask whether the enhancement matches what the phase angle would do to dust of plausible sizes, and whether the color of the light changes in a way that points to different grains or new gas dominating the glow. In quieter geometry, when the comet is farther from the sun and from our line of glare, the coma calms and the chance to catch the nucleus signature improves. That is the season we wait for to make the best estimates of size and spin. For 3i Atlas, the calendar suggests that our most honest measurements will come in the months after the harshest light, when the traveler is dimmer, but the contrast is friendlier. The trade-off is real. We exchange raw brightness for cleaner separation of parts. That is a bargain worth making. Most big misunderstandings are born when we insist on answers at the brightest moment, not at the clearest one. There is one more piece of the illusion that matters. We are primed to think bigger coma means bigger body, because we imagine a reservoir that must match the output. In truth, the efficiency and composition of the surface control the show. A small vent tapping a fresh pocket of volatile ice can run like a geyser compared to a broader area sealed under a dust crust. If the mantle is broken by thermal stress or by micro impacts, a little comet can act for a while like a larger one. The coma's drama reflects the state of the skin, not a simple bucket volume. You can see why experienced observers flinch when they hear size. Claims built on coma alone. All of this may sound like we are hiding behind caveats. I do not think so. I think it is the right kind of honesty. The educational core here is simple. Comets are laboratories where sunlight writes on ice and dust in real time. The writing is legible, but you have to learn the script. You have to understand why angles matter, why grains of different sizes paint different halos, why the same nucleus wears a different face when a vent wakes up or goes quiet. If that feels like a lot, that is because it is. Real objects resist neat labels until you have earned them. Hold one thought as we step forward. The size of the nucleus will settle into a respectable range when the coma lets us see closer to the core, and when models tested against multiple nights agree with one another. The spin will announce itself either in a light curve that stands above the noise or in repeating structures in the inner halo that mark a turning surface. If neither gives up quickly, that is not an omen. It is a cue to keep watching. The sky often pretends to be stubborn when the truth is that we are rushing it. There is a natural place to go next. If size and spin are hard because the coma hides the nucleus, we should talk about the light inside that haze. The colors and lines stitched through the glow are our best clues to what is leaving the surface and how it behaves under the sun. That means chemistry. It means the care we must take with words that run ahead of evidence. It means learning how to say what the spectrum allows without borrowing answers we have not earned. When people hear the word interstellar, their first question is not about orbits, it is about ingredients. What is 3i Atlas made of? In astronomy, we answer that without touching the object. We let light do the traveling for us. The method is older than any spacecraft and humbler than any headline. You collect the glow and the reflected sunlight from the coma. You spread that light into its colors, and you look for fingerprints that atoms and molecules cannot help but leave. If this sounds like alchemy, it is only because the tools are quiet. A prism, a grating, a careful detector, and a disciplined habit of subtraction. The sky writes in thin lines and broad bands. Our job is to read slowly. Two kinds of light matter most for a comet's chemistry. The first is reflected sunlight, shaped by dust grains that act like tiny mirrors, and by ice that can be bright or dull depending on texture. The second is emitted light from gas that has been energized by the sun and by the space around it. The coma is where both live. That makes it useful and messy. Useful because the coma is the place where fresh material from the surface spreads out and speaks. Messy because most of what we see is happening in that cloud, not in the solid nucleus beneath it. You cannot pin a label to the rock by measuring the fog alone. You infer, and then you test the inference with better angles and other colors. There is a familiar alphabet for cometary gas. In the visible part of the spectrum, families of carbon often announce themselves. Simple fragments and radicals like Cn and C2 carve narrow features on a flat background. The family of emissions around green light can turn a halo the faintest sea glass color, a glow that camera sensors exaggerate. But that speaks to well-known processes. None of these, by themselves, proves complex biology. They show that carbon is present in forms we expect, when sunlight and vacuum break more complicated chains apart. In the ultraviolet, the daughter of water, OH, tells on its parent. When ultraviolet from the sun strikes water vapor in a coma, it pries it apart, and the fragments sing in a way we can measure. In the infrared, certain ices and silicate dust, warm enough to glow, will trace out broad features that have taught us as much about dust grain sizes as about composition. These are the honest workhorses of comet chemistry. They are less romantic than big claims and much more durable. If you have heard people leap straight to amino acids, breath, and take a step back, a spectrum taken from far away, through a cloud of dust and thin gas and starlight, is not a mass spectrometer sitting on a lab bench. Distinctive, complex molecules have crowded signatures, and the coma is a busy place where light from many sources overlaps. On rare occasions, spacecraft that flew through a coma and tasted it directly reported molecules that turned textbooks into lively debates. That kind of result is built on proximity and on instruments that isolate single compounds in their own lanes. From the ground, or from a distant telescope in space, the honest way to talk is modestly. Evidence consistent with organic material is responsible. Naming specific complex molecules before the data can carry that weight is not. There is a second caution that belongs on the table. Even the lines we know well can be faint, and faint lines are the first victims of everything ordinary. A slightly unsteady atmosphere, a nearby star whose light bleeds into the spectrum, the subtle imprint of our own air, which must be modelled and removed to reveal the sky's true voice. On a long night, you can hear the observing team repeat little vows to themselves about calibration, because they know how easy it is to be fooled by a reflection or a ghost in the optics. I say this not to make the task sound impossible, but to remind us that chemistry from afar is a discipline. The most valuable words in a spectrum are often not the molecules in the caption, but the sentence that says how sure we are and why. 3i Atlas presents both help and hazards to the spectroscopist. Help, because the coma appears active at distances where some comets still sleep, which improves the chance that gas signatures ride above the noise. Hazard, because activity means variability. When vents open and close, when dust grain sizes shift with time and sunlight, the mixture of light sources in the coma changes too. A spectrum taken on Monday and a spectrum taken on Friday can tell two different stories about the same traveller, not because anyone was careless, but because the object itself is dynamic. The right response is not to average the stories until they are bland. It is to watch the changes and tie them to the distance from the sun, to the angle of illumination, and to hints of rotation. Chemistry in a comet is not a list of ingredients. It is a process running in real time. If we want a way to think about the problem that is both simple and deep, consider color. Not the color that your eyes perceive in an image, which cameras and processing can distort, but the distribution of light across wavelengths when dust dominates versus when gas takes the stage. Dust often makes a coma look redder than the sun at optical wavelengths, a signature of small grains scattering light. Certain gases add narrow features that do not respect that broad trend. Change the mix of the two, and the color changes. Measure color at several distances from the nucleus, and you can tease apart the zones where dust rules from the zones where gas does. It is not as glamorous as declaring a molecule with a long name, but it is solid. Shift from optical to infrared, and the physics changes again. There, warm dust and certain ices glow in their own voice. Their features are wider and lower in contrast, which is harder on a noisy night, but more forgiving of small calibration errors. The practical lesson is that chemistry is not one spectrum or one color index. It is a canvas you build up over time, with many thin coats, letting each layer dry before you add the next. Water, because we need it to think about life, carries a special burden of interpretation. The coma we measure is not a bucket we dip into the nucleus. It is the aftermath of sunlight playing on the surface and in the thin atmosphere of released gas. The ugliest mistake we can make is to equate an early detection of water's fragments with a detailed inventory of ice inside the rock and dust. In truth, sunlight reaches layers differently as the object rotates and as the season changes along its path. A surface crust that suppressed water early can crack and relax nearer to the sun. A vent that favors one volatile can exhaust its pocket and hand the stage to another. In some interstellar comets, we will find what looks like familiar water behavior with unfamiliar ratios. That is exciting. It also means that any sentence with the word pristine should be earned with more than enthusiasm. There is a healthy argument, whispered more often than shouted, about the role of machine learning in reading spectra like these. Pattern recognition is how all of us begin, and clever models can help separate signal from noise, but models learn what we teach them. Feed a prior that expects certain molecules to be present, and you invite a confident answer even when the data cannot support it. I will use tools that make me more careful, not bolder. I want cross-checks between instruments and teams. I want the same line to be seen on another night at a slightly different angle. I want to know how a feature changes when the comet brightens for geometric reasons alone. If an algorithm helps me organize those questions, good. If it hands me a trophy before the race is run, I will set it down. Here is an educational note I carry from comet to comet. When a spectrum is clean and the lines are clear, that is a gift. When the lines are faint and the background complicated, the most valuable product is often not the claim, but the upper limit. It is hard to love an upper limit in public. It feels like choosing vegetables over dessert. But an honest limit tells you that if a species is present, it must be below this level under these conditions. That pins theory to a wall in a way that a loose claim never does. For 3i Atlas, a handful of well-measured limits across several parts of the spectrum may become the backbone against which more speculative ideas must lean. My opinion, and I will say it plainly, is that the most satisfying path through the chemistry of 3i Atlas is the slow one. If a dramatic molecule announces itself with clarity and survives the gauntlet of independent confirmations, we will have the joy of updating our stories. If what we see instead is a sturdy suite of carbon-bearing emissions, water family fragments, and dust features that shift with angle and distance, we will have the satisfaction of watching nature behave as a working laboratory rather than as a billboard. I would be happy with either outcome because both teach. One enlarges our library of possibilities, the other deepens our understanding of how the familiar plays out under unfamiliar origins. There is also a place for those of you who are not sitting at a large observatory. Small telescopes with modest spectrographs can record broad color trends and, under good skies, pick up the stronger bands in bright comet. Coordinated campaigns in which many observers at different longitudes watch the same object on the same nights can stitch together a continuous record that a single site cannot. Even careful broadband photometry, when done with attention to calibration stars and repeated sequences, helps separate nights when dust dominates from nights when gas does. The best science invites many hands, and interstellar visitors pass too quickly and behave too personally for any one team to claim the whole story. Every chemical clue we collect must be read in the light of geometry. The alignment that makes late October difficult from Earth does not mean the object falls silent. It means the light that matters to us is buried in the sun's glare from our point of view. Instruments elsewhere, in orbit around another world or riding in space, where the angle is kinder, may still hear what the coma has to say. Planning for that is part of the chemistry, not an afterthought. If we know a particular line strengthens at certain angles or distances, we design our attempts to catch it when and where chance allows. If you are waiting for a sentence that says exactly which complex molecules live in 3I Atlas, you will not get it here until the sky gives it to me first. That is not coyness. It is the discipline that keeps a documentary honest across many nights and many voices. The language I will keep using for now is simple. The light we have so far is consistent with the kinds of carbon and ice behavior we expect when sunlight wakes a volatile surface in a low-gravity vacuum. The details will change as the distance changes and as the object turns. Any claim that runs faster than that must be tied to a spectrum so clear that it can hold its own without decoration. There is one last reason to embrace careful words. Chemistry is where many stories try to cross the line, from interesting to sensational. It is easy to bolt a meaning onto a molecule. It is harder and more beautiful to let a molecule be exactly what it is and nothing more. A fragment of carbon singing in green light is not a message. It is a physical system doing what physics says it should do, in a place and at a time that we are lucky enough to witness. If, down the road, a pattern appears that demands a new category, we will name it then. Until that day, the best promise I can make is to carry the same patience through the chemistry that we brought to motion and size. We are about to enter a stretch of sky where patience is not optional. The sun will own the stage, and 3I Atlas will move through the brightest aisle of the theatre. That does not end the story. It changes the way the story is told. The next chapter is about geometry and glare, about how a perfectly ordinary star can blind us to an extraordinary visitor for a little while, and about the strategies we use to keep learning anyway. There are nights when astronomy feels like walking into a bright room and trying to admire a candle. The candle is there. It is steady, but the glare from the windows overwhelms everything you hope to notice. Perihelion is that bright room. The traveller we call 3I Atlas bends around the sun in late October, and the line that connects our eyes to the object runs too close to the star that lights our days. The word for this is small elongation, the angle between the sun and the target as we see them. When that angle shrinks, contrast collapses. Even excellent telescopes, even careful detectors, record more of the sun's scattered light and less of the comet's own voice. The most revealing physics may be happening at that very moment. The practical view from Earth is a wash of brilliance that drowns the subtle. This is not a failure of will. It is geometry doing what geometry does. Imagine the solar system as a floor lit by a single lamp in the center. Most of the time, we admire things from across the room, catching their edges in comfortable light. Near perihelion, the object moves into the lamp's halo from our point of view. Our atmosphere adds another layer of difficulty. Daytime sky is a blue veil of scattered photons, and even the deep dusk that hugs the sun holds too much light for long, clean exposures. The air column near the horizon is thick, bending and blurring what you hope to steady. Compromise piles on compromise. Tracking a fast, faint object close to the sun in a bright, unsteady sky is the observational equivalent of threading a needle while riding a train. The phase angle plays its own trick. When sunlight pours from behind the comet toward us, the smallest dust grains are pushed into a regime where they scatter light forward very efficiently. Forward scattering can make a coma flare dramatically. It is a real effect with real science inside it. because the amount of enhancement speaks to the sizes and textures of the dust. It is also a visual illusion that tempts us to misread the size or vigor of the nucleus itself. In other words, the comet may look most dramatic precisely when it is least honest about the core we want to measure. Perihelion is a masterclass in learning to separate theatre from structure. The curtain is gorgeous. The stage is slippery. There are tools that try to turn the sun's brightness into an ally. Coronagraphs hide the solar disk behind an artificial moon, letting the faint neighborhood around it emerge. Spacecraft devoted to watching the inner heliosphere carry such instruments for reasons that have nothing to do with comets. Their job is to monitor the solar wind and the violent events that ride on it. But a bright, dusty object near the sun will sometimes wander through those fields of view and leave a trace, a faint, moving signature in the stream of images that watch our star breathe. Comet watchers have learned to check those data sets during conjunctions, not because the geometry is perfect for chemistry or shape, but because any glimpse is better than none, and because motion itself remains a strong clue. A small arc traced across a coronagraph's panel on successive days is proof of life when the ground is blind. Radio work changes with this geometry as well. In principle, a body that passes between us and a radio source can modulate that background, but the glare that ruins optical contrast does not vanish in the radio. The sun is a powerful radio emitter. Near conjunction, the spectrum is busy, and clean baselines are hard to find. Planetary radar is another dream people love to mention, the fantasy of pinging a traveler and reading the echo like a bat. The practical limit for radar is distance and size together, and a small nucleus far from Earth is an uncooperative target. When you add a geometry that pushes the beam near the sun, even the most ambitious system becomes a lesson in what not to promise. So we bend. We look from somewhere else. This is where the calendar we built in earlier chapters becomes a plan rather than a list. While Earth sits in poor seats, the neighborhood around Mars offers a kinder angle. Cameras strapped to orbiters around that world do not fight the same glare at the same time. A spectrometer there can watch the coma without the sun in its eyes. A wide field imager can catch the changing shape of the tail as the solar wind tugs at it from a direction we cannot appreciate from here. Instruments tuned to ultraviolet light can listen for the daughters of water and carbon in a sky that is dimmer, cleaner, and stable for longer stretches. None of that turns Mars into a magic window. It turns Mars into a plausible workaround, a second vantage that fills the hole our geometry digs. Near the sun, the plasma that fills space picks up energy and structure. Magnetic fields reconnect, streams collide and roll. A comet moving through that weather will carry a tail that records the same story in its lines. There is a kind of dance that happens when the tail disconnects in a sudden wave and then rebuilds itself in the flow. The choreography does not require exotic causes. It is the known behavior of dust and ions caught in a moving field. But catching that dance takes cadence. You need sequences of images close together in time and wide enough in view to see the break and the regrowth. The inner heliosphere images are good at wide. Mars orbiters are good at cadence. Between them, and with a little luck, the perihelion days can leave a record that our ground-based telescopes will later interpret with much more confidence once the glare is gone. The strangest part of the geometry squeeze is psychological. Perihelion feels like the moment when everything should be knowable. The object is closest to the sun. It is warmest. If activity is going to surge, this is when nature will write its most expressive lines across the coma. And yet, for us on Earth, this is the worst time to learn the most obvious things. That mismatch breeds impatience. Headlines crave a verdict when a careful voice should be saying, "We will learn more soon, but not today, and not from here." Living with that gap is a skill. Filling it with guesses dressed as conclusions is a habit we can unlearn. There are practical strategies for squeezing a little more truth from bad angles. Twilight spectroscopy, where an observatory starts as early as safety allows or stays as late as the horizon permits, can catch a sliver of sky where the sun is not yet fully dominant. The exposures are short, the calibration heavy, and the signal to noise a fight in every pixel. But repeated over many mornings and evenings, such efforts can stack into a useful record. Polarization measurements, which track how light's orientation is twisted by scattering, sometimes hold steady even when brightness wobbles. The way polarization changes with phase angle teaches us about the dust in a way less sensitive to total flux. In both cases, the price is patience. You accept that any single session may look thin, and you build value by persistence rather than spectacle. The other honest tactic is to plan for after. The sky rewards those who think one season ahead. If you know that the best contrast will come weeks later, you do what you can now to prime the analysis you will do then. You write down what would count as a real change in the comet's composition. You decide which filters, which slits, and which exposures will be most informative for a dimmer, cleaner object. You coordinate with other sites to cover gaps in weather and latitude. You talk to the teams who work in wavelengths you do not, so that when color shifts appear, you can triangulate whether dust grain sizes evolved or whether a different gas took the stage. The best manuals for blackout weeks look dull to outsiders. They are lists of calibrators, check stars, and housekeeping commands that keep instruments honest. They also make the difference between a pretty picture and a measurement you can defend. It helps to remember that the object does not care when we can see it. It will do what the sun and its own materials instruct. If a fragment breaks free, if a vent carves a new channel in the skin, if the tail peels and reconnects under a shock, the event will not pause for applause. Some of those changes we will miss in real time. Others we will infer from what is different after. A subtle shift in the color of the inner coma can signal a new dominance among the ices. A change in the shape of a brightness profile can whisper that the jet we did not watch ignite has gone quiet again. People sometimes shrug at such inferences because they lack the drama of a live broadcast. I feel the opposite. There is a quiet thrill in reading a scene after the actors have left and understanding what must have happened from the props they forgot to clean up. If the geometry makes Earth a poor witness, it does not silence every ear we have in space. Instruments designed for the sun can still, on the right days, see a traveler flash across their frames. Spacecraft not meant for this purpose sometimes hold cameras that can be repurposed in a pinch. The art is coordination. Teams that build their lives around the star at the center can be forgiving hosts for a comet audience if asked early and respectfully. They know when their schedules breathe. They know when a secondary pointing might be possible without risking the main mission. Nobody has to own the whole story for a shared story to emerge. The best interplanetary science in the last decade has been built on that truth. There is an educational thread running through all of this that is worth holding tight. Resolution is not the same as contrast. You can, in principle, resolve a small structure and still fail to see it because it is hidden in a blaze of light. Dynamic range is as real a limit as the width of an optical path. Cameras and eyes both have thresholds beyond which a faint thing cannot be pulled from a bright background without introducing lies. Good observers learn to love the limits because they keep them honest. They also learn to ask questions that do not demand the impossible from an instrument at the worst time. If you cannot measure a nucleus near the sun, do not pretend you can. Measure the way the coma brightens with phase instead, and tuck that curve away for the day when you will subtract its effect from your estimate of size. Let me say plainly where my own judgment lands in these weeks. I would rather have a well-planned absence of data than a gallery of almosts. I would rather be explicit about what the glare prevents than theatrically turn noise into a narrative. The universe offers so many genuine surprises that we do not have to manufacture them. With 3E Atlas, the surprise is already written into the calendar. We will not see clearly when curiosity shouts the loudest. We will see clearly when patience has had time to work. That is not a defeat. It is the price of learning under a single bright star. When the object rounds the sun from our point of view and the elongation grows, the sky will begin to glow. The halo will fade enough for detail to reappear. The forward scattering enhancement will soften, letting dust and gas return to their usual balance in the light we collect. The instruments we left cooling and calibrated will come out to play the way they were meant to. It will feel like a friend stepping out of a backlit doorway into recognizable light. We will count that as the beginning of our best work, even though it happens after our instincts wanted the finale. There is one more grace hidden inside the squeeze. Because Earth's view is poor, every attempt to watch from somewhere else becomes more valuable. The value is not just scientific, it is cultural. We remember that the solar system is not a postcard pinned on a single wall. It is a place with many balconies. When a camera near Mars, or an imager studying the sun, or a small telescope at a remote latitude catches a moment we could not, the lesson is that knowledge is a communal act. The fact that geometry forced us to share makes the sharing sweeter. All of these points naturally point toward a question that has been hovering at the edge of our plans since the beginning. If Earth's sightline is compromised while the traveler is at its most revealing, what can the red planet teach us from a better angle? What would a camera circling Mars be able to record that we cannot? And how do those records change the story we will tell when the glare finally lifts? From Earth, late October is a glare problem. From Mars, it is a geometric gift. The same curve that pushes 3-eyed Atlas into daylight from our point of view lifts it out of the sun's worst halo for machines that circle the red planet. That difference is not subtle. It is the kind that turns a season of waiting here into a season of watching there. If you imagine the solar system as a stage and the sun as a white spotlight at the center, Earth is stuck in the front row with its eyes full of brightness, while Mars slips into a side balcony where the light is kinder. The traveler is still the same, only the angle changes. In astronomy, angle is often destiny. What can a camera from another world give us that our own ground cannot? First, contrast. When the line from observer to target makes a larger angle from the sun, the sky is darker and the object is not drowned by scattered light. A modest instrument with a steady platform and long, uninterrupted exposures can pull out a faint halo that would be invisible at home. Second, cadence. An orbiter can watch the same patch of sky multiple times per day without fighting weather or sunrise. That continuity is precious during weeks when 3-eyed Atlas is changing its distance and the solar wind is changing its mood. Third, parallax. A view from a different world turns the path across the stars into a slightly different curve. With two curves measured carefully, motion that looked like a single line from Earth becomes a 3-dimensional gesture you can solve for more precisely. The math is old and the effect is small, but every % of precision in a busy coma is worth the effort. In practice, an observing day around Mars divides into two archetypes. There is the dark side pass, when the spacecraft looks outward from the planet's night hemisphere, free from direct sunlight glinting off panels and optics. That pass favors long integrations and faint structures, especially in the outer coma and the dust and ion tails. Then there is the limb pass, when the camera skims the edge of Mars and aims into space from near the planet's thin atmosphere. Geometry can help with stray light control and offers a stable thermal environment because the spacecraft is not constantly cycling between hot sun and cold shade. Neither pass is magic. Both are ways to wrestle a little more signal from a target that insists on staying near the star that blinds us. Spectroscopy from Mars orbit brings a second kind of advantage. The thin air means fewer of our own atmospheric lines to subtract, so weak features are less likely to be lost under the imprint of a planet's breath. An ultraviolet spectrometer that looks outward from Mars can listen for the daughters of water without the heavy veil our sky lays over those wavelengths on Earth. An infrared instrument can catch the broad shoulders of warm dust and simple ices in a band where our home atmosphere is fussy and full of its own signatures. Even a coarse spectrum, taken with modest resolution, can say whether the glow close to the nucleus is dominated by dust, reflecting sunlight, or gas emitting its own. That distinction sounds academic until you try to separate coma brightness from nucleus size later. Then it becomes the hinge of a better estimate. Wide field imaging is where an off-Earth vantage can do something Earth rarely can during conjunction. A camera with a large field can follow the tail for millions of kilometers in a single frame, watching how its shape responds to invisible weather. When a wave in the solar wind passes the comet, a tail can disconnect like a ribbon cut by a blade, the severed section drifting away while a new strand grows from the coma. That choreography has been seen many times, but each object and each solar season draws it a little differently. A sequence of images over days, taken from similar geometry, can time the cut, measure the speed of the drifting piece, and estimate the conditions that force the change. It is like diagnosing wind from the way a flag snaps and curls when you cannot see the air itself. There is also a simple but underappreciated power in having two clocks. If Earth-based observers snatch a glimpse in dawn or dusk twilight at the same time, Mars orbiters are recording a longer look from a darker sky. The pair can be stitched into a continuous record. Many questions about activity need continuity rather than single snapshots. Does the inner coma brighten smoothly or in pulses? Do jets appear in one quadrant, rotate with the nucleus, and then fade? Or are they random and short-lived? The combination of short Earth glimpses and longer Mars sequences can answer those questions even when neither alone would be enough. One strength covers the other's weakness. That is the essence of good campaign design. Some of the most useful data a Mars platform can deliver during the Earth blackout weeks will not be pretty pictures. It will be numbers about the background. Stray light from the sun near the field of view can create ghosts and gradients that masquerade as real structures. Teams that live with the sun all year know how to measure those ghosts. They know which angles make a flare and which settings tame it. If they share that map, it becomes part of the correction our community applies later when we compare brightness profiles across instruments. In other words, even the nuisances of imaging near the sun can be turned into assets if they are measured and reported with care. None of this means Mars will hand us answers without cost. An orbiter is built for its primary world, not for a visiting comet. Its cameras have limits. Its pointing schedule is a ratio negotiated weeks in advance among many needs. Sensors that excel at looking down may have to work hard to maintain stability when they look out. Star trackers that keep a spacecraft oriented may prefer not to stare near the sun at all. Engineers who keep their machines alive are rightly conservative. They will protect their assets first and entertain special observations only when the safety case is sound. That is as it should be. The role for a comet team is to meet those constraints with flexible requests, to ask for the simplest settings that deliver a scientifically valuable return, and to fold whatever we receive into a larger picture without complaint about what we did not. There is a clear educational lesson hiding in this negotiation. Science in space is rarely about ideal plans. It is about workable plans that respect the limits of machines and the responsibilities of the people who fly them. The headline object in the sky is rarely the main customer for a spacecraft's time. A successful Mars window effort will be built from modest, repeatable observations rather than spectacular one-offs. The goal is not a poster image. The goal is a clean set of measurements taken in a geometry we cannot achieve at home. Measurements that will still be useful when we are back under dark skies and doing the harder work of separating coma from core. If all goes well, what could the Mars window actually tell us about 3i Atlas? It could nail down the shape of the tail when Earth cannot see it, and therefore better constrain the direction and strength of the solar wind that day. It could watch for disconnections and rebuilds, and time their onset in a way that lets solar physicists match them to events at the sun. It could measure how the brightness close to the nucleus changes as the phase angle shifts, information that goes straight into the correction we will apply when we estimate the nucleus size months later. It could listen for ultraviolet signatures of water family fragments and track whether their relative strength rises smoothly with solar distance or jumps in steps when vents open. It could sample the inner coma color across several days and see whether dust of one size begins to dominate as the traveler warms, a clue to the surface layer being stripped away. None of these answers declares intent for a rock and ice body. All of them make our later inferences stronger. There is a kind of stereo possible when you mix a Mars view with a trickle of Earth data, and if lucky, a few frames from spacecraft built to watch the sun. The lines of the tail are not flat in the sky. They have depth and curl. Watching from 2 points lets you recover some of that depth. You do not need a fancy reconstruction to get value out of the exercise. Even a coarse sense of whether a kink is a real bend in space or a projection effect can protect you from bad storytelling. We have all seen the way a cloud looks like a tower from one angle and a sheet from another. The coma and tail are clouds made of grains and ions, and they are no less sensitive to the mischief of projection. My own view, and I speak it plainly here, is that the Mars window is worth more for what it keeps us from guessing than for what it might prove. It buys us humility on the days when headlines would otherwise fill the gap with imagination. It replaces a season of hot takes with a season of patient watching. That tone matters. It sets an expectation with the audience that learning is a rhythm, not a reveal, that interstellar visitors do not oblige our schedules, and that good answers sometimes arrive by way of a neighboring world's cameras. For people following along at home with small telescopes who will not be pointing anything at Mars, there is still a role in this window. Coordinating with the timetable of the orbiters, you can plan twilight sessions that bracket their observations. Even if brightness is low and the target small, a consistent series of measurements taken with the same setup and careful calibration stars can show trends that complement the space-based work. Amateur groups have done this to powerful effect in previous campaigns, and the lesson always repeats itself. 10 honest, low-drama data points measured with care are worth more than one noisy attempt to do the impossible. You do not need to see through the glare to add value. You need to be part of a pattern. It is worth marking the calendar in words, not numbers. The early October days around Mars offer the best odds that another world will watch what our world cannot. The late October curve around the sun will keep most of us on the ground in a holding pattern, checking solar images for a passing trace. The first half of November will still be a struggle for Earth's latitudes. The second half and the early days of December will begin to open the sky again before dawn, when the traveler steps out from the brightness and lets contrast return. Somewhere in that timeline, measurements from Mars will cross the void and settle into archives and notes, ready to be compared with what we gather when night at home is friendly again. One final strand belongs in any honest preview of this window. Instruments and teams that work near the sun think in terms of safety margins, dynamic range, and thermal budgets. Those are not the natural language of comet watchers. This is a chance to learn it. If we want help from neighbors, we should be conversant in their concerns. Knowing how long a sensor can stare near the sun without saturating, how often a star tracker needs a clean field to keep a spacecraft stable, or how a small shift in roll can ward off a ghost reflection, turns a vague wish into a feasible request. It is difficult to overstate how much goodwill grows out of a technically literate ask. When the Mars window closes and the comet rounds the sun from our perspective, we will turn back to our own skies with questions sharpened by the data we borrowed. We will want to know whether the inner coma is redder or bluer than before, whether the core looks tighter now that the phase angle is kinder, and whether hints of rotation that were buried in noise emerge as a real rhythm. Those are Earth questions. They are also the inheritance of a season spent watching from somewhere else. A good sequence from Mars does not end the story. It makes the next chapter honest. The sky does not care which planet hosts the instrument that understands it. It rewards angles, patience, and the stubbornness to keep looking when the light is wrong. In the days when our own orbit puts us in a poor seat, it is a relief to remember that we are not the only audience in the theatre. Another balcony is open. A different camera is rolling. And the traveller, indifferent and steady, keeps writing its line across the stage. Soon enough, the glare will loosen. The dawns will hold the object long enough for careful work. The coma will calm. The forward scattering will ease, and the outer halo will thin until the center comes into better focus. That is the season when plans made in the bright days will pay off. When models tuned with Mars-side clues will guide exposure times and filters and the order of our questions. It is the moment when Earth becomes the right place to stand again, and we will be ready to reacquire the traveler with calm hands and cooler skies. When the candle steps out of the window's glare, its flame becomes a line again instead of a blur. That is what the weeks after solar conjunction promise us. The same traveler, three-eye atlas, but seen in friendlier contrast. The angle between our line of sight and the sun grows. The sky darkens around the object. The exaggerated sparkle that forward scattering lays on small dust grains begins to calm. The work that felt like guesswork becomes measurement again. Reacquisition is the quiet craft of picking up a thread that the sun forced us to drop. And December is where that craft comes into its own. This is not a dramatic reveal. It is more like easing the dimmer down in a theatre and letting the stage return to scale. In practical terms, mornings will give us the first chances. The object rises ahead of the sun and lingers long enough in a cooling twilight to allow careful exposures. At first, the sessions are short, the target low, and the air thick with the last blue of night. Each day that follows is slightly better. The arc of visibility climbs, the air mass thins, the line to the sun lengthens. By mid-season, you feel it in your shoulders. The rush to set up before dawn becomes a cadence. You take the same frames in the same order, with the same calibrations, and the sky rewards the repetition. Reacquisition begins before you roll a roof or warm a dew heater. It starts on paper, with a prediction and an acceptance that predictions come with a halo of uncertainty. The last reliable positions from before the conjunction are your anchor. A model turns those positions into an ephemeris, a timetable, and a map that says where to point. The truth is never a dot. It is an ellipse, with axes that widen when you have not measured for a while and shrink as you collect fresh points. On the first clear morning, as you plan for that shape, not for your hope, you build a small grid of fields that cover the uncertainty. You decide in advance how long you will expose, how many repeats you will stack, and how faint you will trust your eyes to go. The plan feels modest. Modest is exactly what you want. Astrometry is the quiet backbone of reacquisition. You measure where the comet falls against the stars, and you report those positions with care. The stars are your rulers. On a good night and a well-tuned setup, the fit of those rulers betrays whether your tracking was as tight as it felt, whether the optics are behaving, and whether the atmosphere added a wobble you must respect. You do not need to wring every fraction of an arcsecond from a small telescope to help. A consistent series measured the same way on multiple mornings is a gift to the teams who refine the path. The ellipse of uncertainty shrinks with each contribution. Pointing for the next week becomes easier. Photometry, the art of turning brightness into numbers, rides on the same stability. You pick comparison stars whose colors bracket that of the coma. You repeat the same apertures and the same sequence. You keep the recipe steady so that any change belongs to the comet and not to you. Tracking is where the first mornings teach you humility. Three-Eye Atlas will be moving. Not fast enough to streak across the field while your back is turned, but fast enough that a long exposure leaves it softened in one direction. You have three sensible choices. You can track the sky and let the comet smear a little, then recover its shape by stacking many short frames along its predicted path. You can track the comet's rate and accept that the stars become trails, measuring your rulers from those trails if your software allows. Or you can split the difference, using exposures short enough that neither object nor stars stretch beyond usefulness. Professionals use all three approaches depending on the night. Amateurs can do the same. What matters most is that you decide before the sky tempts you into improvisation. Clarity wins over cleverness when the goal is a clean time series. If you do not have a large telescope or a sophisticated camera, you still have a role every bit as real as an observatory's. Reacquisition rewards discipline more than aperture. A small instrument used the same way, night after night, can chart trends that swing past a larger instrument that hops between setups. Early December favors dawn runs that last an hour or two. That hour is precious. Use it to build sequences that can be stacked and compared. If you chase the perfect frame, you will miss the value of many honest, imperfect ones stitched together. If you set a pattern and keep to it, the pattern becomes the science. Color carries quiet information in this season. When dust dominates, the coma often appears redder than the sun. When gas brightens relative to dust, narrow features ride on top of that trend. Even simple broadband filters used consistently can show whether the inner coma is warming into dust or cooling toward a gas-rich glow as the geometry relaxes. If you have access to a modest spectrograph, the December weeks are when faint lines start to climb out of the noise again. In the ultraviolet, fragments that betray water's presence may pick up. In the optical, the family of carbon emissions that many comets share can be tracked for changes in strength. In the infrared, broad shoulders from warm dust hint at shifts in grain sizes and textures. None of this requires naming an exotic molecule. It requires patience with a signal that improves a little each morning. Rotation is the drumbeat you listen to while you measure light. On a bare asteroid, you often hear the beat quickly. On an active day, it hides under a blanket. Reacquisition is your chance to tug at the corners of that blanket. You design a light curve as if you expect the object not to cooperate. That means many short exposures rather than a few long ones, repeated sequences at the same times on successive mornings, and an acceptance that the weather will steal a night now and then. The period you seek may be long, noisy, or drifting because sunlight and jets apply small torques. Do not be afraid to combine data across teams as long as the recipes match. A rhythm that fails to rise above the noise on Tuesday may stand clear when Monday and Wednesday sequences are added. Each time you see a swell and a dip repeat, you earn the right to call it a hint rather than a hope. The coma will also play its tricks. Jets can sketch fan shapes and subtle spirals in the inner glow, features so slight that they are invisible on a single image, but show themselves when you subtract a smoothed version of the coma from the original. This is a game for careful hands, not for social posts. You tell your software what counts as smooth, and it obeys, sometimes finding structure where there is only noise, sometimes erasing truth in its zeal to scrub a background. If you try such processing, write down every choice you made and attempt the same with a field star to see how your steps behave when there is no comet at the center. If, after that discipline, you see a hint of a repeating fan aligned in the same quadrant on more than one morning, you may have found the whisper of a vent or the ghost of a rotation axis. The correct tone when you share it is cautious and curious, not triumphant. There is an educational thread that runs through these methods, and it is not a small one. The words apparent and intrinsic live here. Apparent brightness is what the detector sees. Intrinsic brightness is what the comet would show if distance, angle, and all the tricks of scattering were held fixed. December is when you make the leap from one to the other with fewer unjustified steps. You record the phase angle, the elongation, the air mass, and the color of your comparison stars, and you let those notes remind you later why a change was real or was only the sky shifting under your feet. The habits look like housekeeping. They are the bones of honest inference. As visibility improves, you can widen your aim. Early mornings favor small regions around the nucleus where the signal to noise is kindest. Mid-season lets you stretch the apertures and ask how brightness falls with distance from the center. That profile is not a trophy, it is a diagnosis. A steep fall hints at dust that settles quickly or at vents that blow in narrow cones. A shallow fall suggests fine grains lingering, pushed gently by sunlight, spreading the glow. If Mars-side images or a lucky pass through a solar imager, gave us tail behavior during the blackout weeks, your ground-based profiles in December and beyond become the counterpoint. They either rhyme with what we inferred then, or force us to update the way we imagined the scene played out behind the sun. All of this looks, to an outsider, like the quiet routine of astronomy. To those of us who have waited through glare, it feels like a long exhale. The first morning you recover a clean point against the stars. The first time a broad band measurement stacks into a curve that bends instead of flutters. The first night when the tail is a shape rather than a suggestion, you remember why we accepted the blackout instead of filling it with noise. The reward for that patience is not a headline. It is a stronger voice for the object itself. There will be temptations along the way. A sudden brightening may flash in a single sequence. A processed image may hint at a fragment peeling from the coma. A spectrum may show a wiggle where you expected a line. It is good to feel your pulse rise. It is better to ask what other instrument would have to see for this to be real. Could a second camera at another latitude reproduce the change? Does the brightness jump stick to the same aperture when you remeasure, or does it fade when you change the center by a few pixels and repeat the photometry? Did the wiggle survive if you shift the extraction window on the spectrum by a hair? Professionals make such checks in reflex. Amateurs can learn them quickly. The payoff is that your big moments remain big when the community leans on them. There is a place in this plan for everyday wisdom too. Dew will steal contrast as surely as glare. A cable that works in summer will turn brittle in winter and ruin a dawn. An autofocus routine that is perfect on stars will chase its tail on a fuzzy target unless you teach it not to. Reacquisition rewards those who practice the motions in October on easier objects so that December's first morning is not your first rehearsal. Keep a short list next to your setup. Check bias frames, darks, flats, and focus. Confirm the non-sidereal rate has loaded before the sky brightens. Verify that your timestamps are honest, because a light curve is only as good as its clock. Nothing on that list is glamorous. Everything on it is the difference between an image that looks like a comet and a measurement that acts like one. For those who follow along without a telescope at all, December is still your season. The story becomes legible again. You can hear what is discovered in the tone of the voices sharing it. Careful ones will say what changed and how they know, not just what they hope. When a claim grows bolder, listen for the checks it passed. Was the feature present on more than one night? Did teams using different instruments find it again? Are there numbers with it, not just words? That way of listening is its own education. You learn to love the way knowledge tightens when it is repeated under different lights. I will say plainly where my own judgment lands as the sky opens. I prefer measurements that are simple and repeatable over spectacular pictures that cannot be compared with anything taken the next morning. I am happiest when a team shows the same setup used over 6 dawns and the same corrections applied in the same order. Nothing attractive is lost. Beauty in astronomy does not fade when it is measured. It deepens. A faint curve with a steady hand behind it is as moving to me as a dramatic image. Both open the door to understanding. One is easier to trust. In time, as the elongation grows and the comet draws farther from the sun, the season will stretch beyond morning. Evening sessions will come. Exposure times will lengthen. Spectra will grow cleaner. The nucleus, if we are lucky, will leave a firmer signature under a thinner coma. The light curve, if we have been relentless, will stop being a rumor and become a period with uncertainties we can quote without apology. The chemistry, taken in many colors and under many angles, will settle into patterns that either match the familiar or point to a difference we can defend. None of this requires drama. It requires staying in the story. There is a natural question that arises as the data thickens. Why did the path feel so complicated in the first place? Why did the object spend its most revealing weeks so close to the sun from our point of view that we had to beg other worlds for help and trust instruments never built for comets? The simplest answer is geometry. The deeper answer is that 3i Atlas moves against our neighborhood's usual flow, and motion against the grain changes everything you think you know about timing and angles. We're about to spend time with that idea, because it explains not only the observational calendar, but the way the traveler encounters wind and field and light. Understanding it will make December's measurements make more sense. It will also temper the stories that try to turn an unusual lane choice into a motive. Most of what circles our sun keeps the same rhythm and the same direction, like swimmers sharing lanes and pushing off in sync. Planets, most asteroids, many short-period comets, all flow prograde, which simply means they travel around the sun the same way Earth does. 3i Atlas does not. It approaches on a retrograde path, moving against the traffic. That single word retrograde can sound exotic or meaningful in ways it is not. It is a description of orientation, not a verdict about purpose. Think of a highway cloverleaf. If you fly a drone above it, one car can loop the wrong way through an empty ramp and still obey the same physics as every other car. The lanes and the lampposts do not care which way the tires are pointed. What changes is the kind of crossings that happen, the speeds at which they happen, and how long each encounter lasts. Direction matters first because it sets relative speed. The speed of 3i Atlas around the sun is set by gravity and distance, the same way it is for any body on an open interstellar path. But the speed of 3i Atlas relative to a planet depends on whether the planet and the comet are moving with or against each other when they meet. In a prograde encounter, the difference can be gentle, like two runners joining from nearby lanes. In a retrograde encounter, it can be abrupt, like two runners passing shoulder to shoulder in opposite directions. That higher relative speed shortens the time the traveler spends near a planet's neighborhood, which makes gravitational nudges brief and observational windows tighter. It also makes the space around the comet a little noisier. Gas and dust pouring away from the nucleus meet a headwind instead of a tailwind, and the tails they build can be shaped and torn in ways a gentler flow would not encourage. Direction matters next, because it changes angles. The plane that holds most planetary motion is called the ecliptic. A retrograde orbit often slices through that plane at a steep angle. Where the slice happens, the path crosses a line we call the node. Crossing at a steep angle means the comet's path against the starry background changes faster as seen from Earth, and the phase angle, the angle between sun, comet, and observer, swings through a wider range in fewer days. Those changing angles are not symbols. They are the dials that set how bright dust becomes, how easy spectra are to read, and how cleanly a telescope can track without smearing the light into a line. In gentler geometry, exposure times can be long and forgiving. In retrograde geometry, you often choose many short exposures and stack them carefully to follow the target's curve. If you want an everyday picture for retrograde encounters, think about meteor showers. When Earth meets streams of dust that come from retrograde comets, the meteors burn brighter and quicker because the grains hit our atmosphere head-on at a higher relative speed. We see the same family resemblance in the way a retrograde comet's tail reacts to the solar wind. When an ion tail disconnects and rebuilds, the cut can look sharp, the rebuild brisk, not because anything magical is hidden inside the nucleus, but because the environment it is plowing through is more forceful. The physics is ordinary, the staging is dramatic. The inner heliosphere, the region near the sun, is filled with charged particles and magnetic fields that flex and twist over days. A retrograde traveler meets that weather at unusual angles. The consequence for observers is twofold. First, the clock ticks faster on structures. Kinks and waves in a tail can evolve between one dawn session and the next, so cadence matters more than it would for a body sharing the usual traffic. Second, the way brightness changes with phase angle can trick the eye into thinking a nucleus has surged in power when the dust is simply showing off in a favorable lighting geometry. Forward scattering, the way fine grains fling light toward the sun, is stronger when the sun is almost behind the comet from our point of view. A retrograde path that hustles us through those angles quickly will deliver short-lived flourishes that must be read with a careful hand. Retrograde does not mean rare for comets. Many long-period comets approach from all directions, including retrograde, because the reservoirs that supply them are roughly spherical clouds of small bodies far from the sun. Stir one of those clouds in a distant system or in the wide neighborhood around a star, and you can send objects inward from almost any tilt. For interstellar visitors, the distribution of arrival directions should be even less tethered to our plane, because their birthplaces are other systems with their own cloverleafs and their own histories of bumps and throws. That is why retrograde is not a red flag by itself. It is a reminder not to project our local habits onto a guest who learned to move elsewhere. What retrograde does change, reliably, is our schedule and our expectations for how neat the data will be. Tracking rates rise, stars smear if you do not keep exposure times short or shift images along the predicted path before you stack them. Radial velocity, the line of sight speed that nudges spectral lines, swings through its range briskly, which can help confirm you have the target centered in your slit, but can also complicate comparisons night to night. Air mass, the amount of air your light has to plow through, is often worse during the first sessions because the target hugs the horizon at ungentle hours, and retrograde paths near perihelion can make those sessions feel like a race you joined late. None of these are blocks. There are places to lay more boards. If you worry that a retrograde path says something deeper about intent, turn to the numbers we already understand. Planetary encounters happen where the geometry allows, not where stories would like them to. Big planets occupy big lanes. So do worlds with many cameras. When an interstellar body's path crosses the inner system, it is not shocking that some of those crossings come near Mars, or that a later leg will slide past Jupiter's vast sphere of influence. Jupiter in particular owns a huge share of the solar system's gravitational personality. To a traveler, it is a city you pass through, whether you meant to visit or not. What looks, in a script, like a tour can be, in physics, a quick skim past street corners that occupy most of the map. There is another quiet lesson hidden in retrograde motion. It can exaggerate our selection effects. Surveys that scan the sky prefer regions away from the sun, away from dense star fields, and near the ecliptic where many bodies gather. A comet screaming across the sky at a steep angle stays inside a given field of view for fewer hours, and scheduling a return look the next night can be harder because it has run out of the frame and into another team's time. We are more likely to confirm and follow bodies whose paths cooperate with our patterns, and less likely to notice those that do not. When a retrograde traveler still becomes the talk of our calendars, that sometimes says as much about how loud it is in dust and gas as it does about anything unusual in the nucleus. We meet what we can meet. You can map the practical consequences of retrograde into familiar questions. How long will we have a clean look each morning? Shorter than you want in the first weeks, longer later as the elongation grows. How cautious should we be when reading a brightness surge near a small sun angle? Very cautious. Because geometry, not geology, may be doing the talking. How should small instruments be prepared? By practicing non-sidereal tracking, by building short exposure stacks, by repeating the same recipe night after night, and by remembering that consistent limits are precious data when the target plays keep away. How should large instruments be prepared? By protecting time for cadence, by sharing raw frames quickly so that teams at other longitudes can catch the same features from a different angle, by treating retrograde not as glamour, but as a need for speed. There is a human thread running through this, and it is worth naming. Retrograde invites narrative. Against the grain sounds like rebellion. In a story, rebellion belongs to a character with motives. In a documentary, retrograde motion belongs to geometry. My own view is simple. I prefer to save my taste for stories for the places where the data corners us into a real choice. Direction will not be that place. The same tide that taught our planets to share a flow will from time to time send a traveler through the lanes in reverse. It does not need a reason that flatters us. You do not have to be an orbital dynamicist to understand the key angles that make retrograde feel different. Imagine the comet crossing the ecliptic at a slant. Before the crossing, it is above the plane where most planets live. After the crossing, it is below. The angle of that slant is the inclination. A large inclination means fewer days when the Sun, the comet, and Earth line up in ways that make the objects sit high in a dark sky. It also means fewer days when the phase angle dials in a comfortable balance between dust and gas in the light we collect. We get bursts of friendly geometry wrapped in long stretches of compromise. That rhythm drives everything downstream, from the kinds of images that are possible to the kinds of sentences we should be willing to say. There is comfort to take from history. Retrograde comets have been read honestly before. When geometry was kind, we learned their sizes, spins, and surface behavior. When geometry was poor, we kept our claims modest and waited for better nights. Sometimes the result was a surprise, like an outburst where none had been expected, and we wrote new lines in old notebooks. Sometimes the result was exactly what a textbook would have predicted, and we felt relief that nature had kept one of our teachers intact. 3i Atlas will earn its place on that spectrum by doing what it does under light we cannot change. Retrograde will make the ride faster and the edges sharper. It will not make the laws different. You may hear, as this season unfolds, a fresh round of arguments about intent. Why cross near Mars when Earth cannot see? Why round the Sun when our planet sits on the far side? Why drift past Jupiter months later, as if to say hello to the largest world in reach? I think the better way to phrase those questions is to ask how many paths through the inner system avoid those features. You quickly discover that many do not. A glare that hides a traveler from Earth is a common price of passing near the Sun. A brush near Mars happens easily because Mars is often near the part of the sky where we are most interested and where search programs look hardest. Jupiter is difficult to miss from a dynamical point of view. It casts a long shadow of influence. When you start with those base rates, retrograde becomes one part of a geometric recipe, not the spice that changes the dish. There is a practical kindness you can extend to yourself as you listen to debates that swirl around direction. Keep 2 buckets. In one, put what retrograde definitely does for us. It shortens encounter times, raises relative speeds with planets, complicates tracking and cadence, and changes how dust lights up at certain angles. In the other, put what retrograde does not do for us. It does not, by itself, hint at design, intent, or message. It does not erase the need for independent confirmations when chemistry, or spin, or size are debated. It does not license precise numbers where only ranges are honest. If you keep those buckets straight, the rest of the conversation becomes calmer and more interesting. Here is where my own opinion stands, stated plainly and without decoration. I like retrograde because it forces good habits. It makes us plan for cadence instead of relying on convenience. It pushes us to document geometry with each measurement so that we can later subtract lighting tricks from physical changes. It teaches patience in the face of flashy moments near the Sun and rewards the quiet labor of December mornings. That is not romance. It is how a community stays honest under bright light and short nights. Retrograde also nudges us toward better teamwork. A fast-changing target asks for many eyes at many longitudes. People who might otherwise work alone find themselves trading raw frames, comparing instrument setups, aligning photometric apertures, and agreeing on how to quote errors. If a Mars side image or a heliospheric imager catches a tail disconnection while our own sky is bright, it becomes a shared thread that we match to our later ground-based profiles. None of this is automatic. It is a choice to treat geometry as a chance to collaborate rather than an excuse to guess. When we make that choice, retrograde turns from a problem into a teacher. There is one last connection to make before we leave direction behind. Retrograde, with its quick angles and bright tricks, is where stories about improbability tend to multiply. A high inclination, a near miss here, a brush there, a blackout when curiosity peaks. and the mind starts to arrange these as beats in a plot. It is good to feel that tug, and better to test it. The right way to do that is to talk about probability carefully, with base rates in hand, and with an honest eye for the traps that turn ordinary geometry into ore dressed up as statistics. Before we let words like unlikely and impossible set our tone, we owe ourselves a sober look at how easy it is to count only the coincidences we notice, and forget the many paths that would have looked coincidental in different ways. That is the work waiting for us next. When a rare visitor cuts across a familiar sky, our minds do something generous and dangerous at the same time. We gather the striking details and we try to make them add up to a story. The path was retrograde. The Mars window opened just as Earth slid into bad seats. The sun hid the most enticing week in glare. Months later, the curve passes Jupiter's broad neighborhood. Each line feels meaningful on its own. Together, they begin to sound like intention. That is how people slide from geometry to motive. The bridge they cross is built from words like unlikely and almost impossible. Before we let those words carry us, we owe ourselves a slow walk through what probability really means when we use it to read the sky. Probability is not magic. It is a way of keeping honest books about uncertainty. To do that job, it needs three things that casual conversation rarely supplies. It needs a precisely defined event. It needs a clear description of the space of possibilities you are willing to count. And it needs transparency about the assumptions that generate those possibilities. In plain language, if you want to say the chance of some feature is small, you must be able to answer three questions without waving your hands. Small compared to what? In which universe of cases? Under which model of how those cases arise? Without those answers, a small number becomes theatre. With them, a small number can be knowledgeable. Start with the event you want to measure. If you say it is suspicious that perihelion arrives when Earth sits on the far side of the Sun, you must decide what would have counted as equally suspicious if the date had been different. If you had only called it remarkable for this one alignment on this 1 week, then you have a thin target, and a tiny chance might be real. But if you had called it remarkable for any arrangement that made Earth's view bad at the time of peak activity, across a wide range of dates, you would have drawn a thicker target after the arrow hit the board. That is the Texas sharpshooter's favorite trick, painting the bullseye around the bullet hole. Probabilities that pretend the target was fixed, when it was, in fact, flexible, are not wrong in arithmetic. They are wrong in honesty. Now define your space of possibilities. In orbital problems, there are many ways to do that. You can average over all paths that arrive from all directions, with speeds drawn from a plausible interstellar distribution. You can restrict the subset that crosses the inner system within some number of months of the date you are excited about, because that defines the epoch during which your surveys would have noticed the object. You can condition on brightness, or on activity UI, or on inclination. Each choice changes the denominator in your fraction, which is the count of ways the world could have gone. That denominator is not decoration. It is the stage on which your event happens. Expand it, and your rare event becomes common. Shrink it, and your common event becomes rare. You must say which stage you chose, and why that stage deserves to be called the world. Assumptions run under all of this like pipework under a floor. If your model assumes that interstellar visitors arrive with no bias in direction or speed, you should say so. If your model acknowledges that our surveys see some directions more than others, and some rates of motion more readily than others, you should say that instead. If your model silently inherits the search pattern of one specific survey that sleeps during parts of the year, or avoids bright fields near the galactic plane, you should say that too. Assumptions can be clean and still be wrong. What they may never be is invisible. Hidden assumptions turn probability into a costume for preference. Good assumptions turn it into a tool. When people invoke tiny odds to claim a pattern, they often skip all three steps. They define the event as the precise outcome we saw, and no other. They chose a small world of alternatives that would not have drawn much comment, and they bury assumptions about how paths are distributed and how instruments look. That recipe produces numbers that sound dramatic and travel well. It also produces certainty where only appetite lives. If you feel defensive as you read this, you are not alone. We are storytellers by nature. We love the feeling of the rare bird landing on our fence the day we looked out the window. The discipline is to admit how many birds would have counted as remarkable if they had landed instead. There are two base rate ideas that pull a lot of weight in cleaning up our thinking here. The first is answering the question, what fraction of all possible inner system paths for interstellar bodies would make Earth's view of perihelion poor? Not which exact day and angle we got, but any day and angle that would have hidden the candle. If that fraction is not tiny, the surprise drains out. The second is answering, what fraction of all plausible paths would brush near Mars and later pass within Jupiter's wide reach? Not as spectacles, but as ordinary byproducts of how much real estate those worlds occupy in phase space. You may find that the shapes you treated as rare are simply the shapes that fill the room. Base rates are the background noise you must hear before you can recognize a melody. We also carry a weakness for counting only the surprises that happened and forgetting the many that could have happened and did not. This is the look elsewhere effect with a friendly mask on. If you invite your attention to tilt toward anything that feels conspicuous, you should not be shocked when something answers that invitation. It is the birthday problem in a different suit. In a small group, the chance that someone shares your birthday is low. The chance that some pair shares a birthday is much larger. In a calendar full of observing windows and planets, and spacecraft and glare and fast motion, the chance that some pair of circumstances will rhyme is not small. We notice the rhyme and treat it as a plot point. The universe, faithfully random under a set of rules, shrugs. Selection bias is another way the sky plays tricks on us with our help. We detect what we are built to detect, and we linger on objects that cause a stir. A quiet, dim visitor that crossed the inner system at an uncooperative season will not become a household name. A loud, dust-rich visitor with a strange tilt that chooses angles we find dramatic will be tweeted and debated for months. Then, months later, someone will count the times our talk turned toward triangles in the sky and declare that triangles are suspicious. The selection with which the object chose us is real. The suspicion we build from our own attention is not. If this sounds harsh, consider how many interstellar bodies we missed before our surveys were fast and systematic. The ones we catch first will always be an odd sample. That is what it means to stand near the door of a party and form an opinion before everyone has arrived. We should also talk about the difference between pre-committed and post hoc claims. A pre-committed claim is a prediction made before the data arrive, detailed enough that we would agree, in advance, that the test counts. If you say, if the geometry hides perihelion, then we will see a certain shape in the tail from another vantage and not otherwise. That is a prediction. A post hoc claim is a story written after the events, dressed as inevitability. It is not wrong to write such stories. It is wrong to treat them as strong evidence. The right way to turn a post hoc feeling into knowledge is to write down the next prediction in advance. If you suspect that visitors with certain features will deliver a specific sequence of angles and close passes more often than chance, publish the rule and wait to be right or to be corrected by the next few arrivals. That humility seals the leak through which our love of narrative pours into our use of numbers. There is one more family of traps that deserves daylight. We are poor at judging independence. We like to treat a chain of events as a string of separate odds multiplied together. The chance of A and the chance of B and the chance of C multiplied gives a tiny number that feels like fate. But in orbital geometry, many of the things we care about are not independent. A path that produces a small sun angle at perihelion, as seen from Earth, often drags with it a set of seasonal alignments that make Mars a good witness. A high inclination that swings us through a rapid change in phase angle also makes forward scattering enhancements more likely. Multiply these as if they were separate roulette wheels, and you conjure drama out of a mechanical relationship. The right move is to measure the joint chance directly under a model that acknowledges the links. The wrong move is to pretend the links are not there so that the product may shrink. Let's ground this in the traveler at hand. We can ask how surprised Toribe was about the sequence, sometimes framed as a tour. Early October favors Mars for a view. Late October puts Earth in the glare near perihelion. March lays a leg near Jupiter's realm. What is the real claim we are weighing? Not that this exact sequence, with these specific dates, is interesting, but that any set of windows that burdens Earth and empowers another platform and brushes a big planet is too tidy to be chance. That is the shapeless assertion that requires shape before it can be tested. Make it crisp. Fix the windows you would accept as similar. Fix the threshold for what counts as near. Fix the time span over which you would count the hits. Fix the distribution you will draw test paths from. Without those choices, there is no denominator. With them, there is a check you can run. If that check says the sequence is not rare, you must let go of your surprise. If it says the sequence is rare under reasonable assumptions, you have interesting work to do, not a solved mystery. Bayesian thinking is one way to carry these disciplines without drowning in jargon. In that frame, you remember that your belief before the data matters, and you update it afterward by how strongly the data favors one hypothesis over another. If your prior that an interstellar visitor is a natural comet is very high, it will take data with a strong likelihood ratio to tilt you away from that. A single geometric coincidence will not do it. A pre-specified pattern that repeats in future visitors and is hard to reconcile with the natural model might. This is not playing defense for any worldview. It is honoring the idea that extraordinary claims require extraordinary evidence by making the word extraordinary do real work. A feeling of strangeness is not extraordinary. A pattern that resists natural explanations in experiment after experiment is. At this point, some people throw up their hands and say that probability is squishy and that the numbers can be made to say anything. That is not my experience. Sloppy probability can be made to say anything. Careful probability trims stories to fit what we can defend. It does not end the debate, it sets the terms. If you doubt that, watch how quickly a community converges on standard ways of quoting uncertainties after a few seasons working on the same kind of object. Photometrists agree on apertures and corrections. Spectroscopists agree on which atmospheric bands must be modeled before a line can be claimed. Orbit calculators agree on which perturbations matter and which can be parked. Those agreements are not accidents. They are the bones of repeatable probability in action. There is a gentler lesson here for bystanders who love the sky but do not live inside the math. You do not need to compute to be a good judge of probability talk. You can ask for clarity about the event, the world of alternatives, and the assumptions. You can ask whether a claim was a prediction or a story after the fact. You can ask whether multiple parts of a dramatic sequence are truly independent, or whether they rise and fall together from simple geometry. You can ask whether base rates have been measured and respected. You can ask whether anyone has tried to break the claim with a null model that reproduces much of the drama for free. These questions do not require a calculator. They require the discipline to be curious without being seduced. Now, turn down the heat and consider how this applies to our household comparisons. Oumuamua taught us that small bodies can act in ways that strain our models. Borisov taught us that interstellar comets can also behave like the ones we already know. 3 Atlas lives somewhere between those poles in the popular imagination because its geometry feels flamboyant. If we carry the probability hygiene we have just rehearsed into that comparison, what happens? We stop counting only the flourishes that please a narrative and start counting the many ways a fast, tilted, dusty visitor could have seemed remarkable in a different register. We stop multiplying linked odds. We start specifying the world in which a surprising sequence would count. and we check against that world instead of against a smaller one we chose because it made a nice number. Most importantly, we stop treating words like unlikely as if they were facts and start treating them as invitations to measure better. My own view is modest and I hope useful. I think the sky is already interesting enough without decorations. I think probability, practiced carefully, protects wonder from turning into credulity. I think the most beautiful outcome for this visitor is not that we find a loophole in physics that only a dramatic story can fill, but that we master the patience to let geometry play out, to test the easy explanations first, to be surprised when they fail, and to be satisfied when they succeed. I want us to be the kind of audience that can be moved by a small correction to a light curve, because it cleans up a false impression as much as by a big claim, because it flatters our hunger for meaning. There is a practical reward for doing this work. When the next interstellar object arrives, and it will, we can carry forward not just better instruments, but better promises. We can write down in advance which alignments would impress us and why, which combinations of measurements would push us to change our minds, which apparent coincidences we will treat as everyday, and which we will treat as flags. We can pre-register our awe. That is not as poetic as living by instinct. It is kinder to the truth, and it ensures that when a genuinely rare pattern arrives, we will recognize it without having to talk ourselves into it. Probability does not dull the night. It steadies our hands while we point the telescope. It makes our joy more durable when a curve we hope to see appears. It makes our disappointment more graceful when a flourish turns out to be lightning. It lets us admire a candle even in a bright room because we have done the work to know how much of the sparkle is the sun and how much belongs to the flame itself. Carry that discipline with you as we turn to the other travelers who taught us these habits, the small scout that outran our certainty and the dusty messenger that reassured it, and you will hear their lessons more clearly when we place 3i Atlas beside them. Every household has a first guest who alters the way the door feels. For modern astronomy, that first guest was a faint sliver that arrived without warning in October of 2017 and bent past the sun like a blade catching light. We named it Oumuamua, a word chosen to mean a scout or a messenger from afar. It came fast, it left faster, and it pulled behind it a wake of questions that we are still tidying. 2 years later, we received another visitor, Borisov, whose behavior felt like a deep breath after a surprise. It trailed a familiar kind of dust and gas, the sort that comets in our own family have rehearsed for us many times. Now there is 3i Atlas, a traveler whose geometry, timing, and bright coma have turned old questions into new chores. 3 guests in less than a decade, each different enough to teach, each similar enough to remind us that interstellar is not a label for a single kind of thing. Lying them side by side is not an attempt to force a story. It is an attempt to see whether their differences rhyme. Begin with the one that left us blinking. Oumuamua was small by the standards of objects that command headlines. It did not broadcast itself with a broad, glittering coma. It offered only the narrowest window for observation, racing away from the sun and toward the dark before many instruments had even acquired its scent. Photometry, the taking of brightness and turning it into meaning, suggested a body whose light rose and fell by a factor that implied a dramatic shape or a surface with strong contrasts. A long triaxial ellipsoid would have done it. A flat chip turning in sunlight would also have done it. Either way, it seemed unlike the rounder, fuzzier visitors we know well. Most unsettling for many readers was the small, non-gravitational nudge in its path that honest astrometry could not ignore. Comets sometimes do that when gas jets push them gently. Oumuamua did not betray those jets in the usual ways. The mix of subtle thrust and quiet chemistry left room for many hypotheses and for more than a little projection. It also left a clear lesson. When you meet a traveler late and watch it briefly, you can learn enough to be intrigued and not enough to be sure. And in that gap, our minds like to decorate. Borisov felt different from the first night. Discovered in 2019, It wore the classic costume of activity that textbooks prepare you to see. A head, a tail, and the kind of spectral features that tell you sunlight is loosening familiar ices and simple carbon families into the coma. It was, by most measures, an honest comet that happened to be arriving from another star. That sentence alone is a revolution. For a century or more, we built our stories about comets out of local examples, and then used those stories to guess about the rest of the galaxy. Borisov let the arrow fly in the other direction. It suggested that at least some of the chemistry and dust physics we have learned at home carries across the void. Not everything was comfortable. Boron was not blinking at us in neon. Amino acids were not waving flags. But the balance of the familiar and the new told us something quiet and strong. Interstellar does not force strangeness, and when you see the ordinary arrive from a far cradle, your faith in the universality of physics grows. 3. Atlas walks a line between those two moods. It is not shy about activity. Its coma announces itself from distances at which many comets would still be clearing their throats. It moves against our usual traffic on a retrograde path, a choice of orientation that complicates schedules and lighting, and tempts scripts to assign it a personality. Its perihelion lands in a patch of calendar that, from Earth, hides more than it reveals, while opening a better seat for Mars. Months later, the path passes by Jupiter's broad realm, the way most long legs through the inner system must do. The combination is striking. Striking is not the same as suspicious. It is the kind of geometry that produces strong reactions in dust and tail and requires a level head in the way we read them. If you stack the three guess and look for a pattern, you can force one. A scout that strained our models, a messenger that soothed them, a traveler whose stagecraft feels theatrical. It is tidy and therefore suspect. The more honest method is to ask what each teaches that the others did not, and whether those lessons complement rather than complete. For me, the complement falls along three axes: how much time we had, how much the coma cooperated, and how our instruments and methods have matured. The first axis is the pace of the encounter. Oumuamua was a sprint. We failed as a community to pay attention to it fast enough to leave us with the data we wish we had. That is not an admission of guilt. It is a record of capacity in a system that was built around other priorities. It struggled to acquire, to share, to translate curiosity into reserved nights and instrument modes. The enduring lesson is not about the object. It is about us. We need ready checklists for rapid targets of opportunity, agreements that say which kinds of observations become automatic when a new interstellar label appears, and pipelines that make raw data useful across teams on timescales of days rather than months. You can see those muscles flex more readily now than in 2017, not because 3i Atlas demanded it, but because Oumuamua trained us. Borisov's pacing was kinder. Its brightness and behavior allowed more routine observing, and that steadiness fed confidence that a new category of object could still submit to old methods. Because the science looked less like a sprint and more like a drumbeat, many observers outside the largest telescopes could contribute measurements that held value. That democratization matters more than people admit. When a story can only be told by one or two sites, the story grows fragile under weather and scheduling. When it can be told by many, confidence grows resilient. In that sense, Borisov was a rehearsal for campaigns that rely on distributed, patient effort. If you see more amateurs and mid-sized facilities building rehearsal schedules for 3i Atlas, that is the echo of 2019 being heard in 2025. The second axis is cooperation from the coma. Oumuamua gave no generous haze for chemistry to sing through. Borisov gave an honest choir. 3i Atlas is louder still, and from farther out. Loudness is not only a gift, it complicates the job of separating the nucleus from the cloud, and it exaggerates lighting effects near small angles from the sun. The educational thread through all three cases is the same, repeated with different emphases. Apparent and intrinsic are not synonyms. A bright envelope does not guarantee a large heart. A fussy spectrum does not guarantee complexity in the solid. A lack of gas lines that you expected does not guarantee their absence, in fact. In each guest, the most useful sentences turned on how carefully observers handled that distinction. In each guest, our habits have improved, if only because beating our heads against Oumuamua's silence taught us the price of taking shortcuts. The third axis is what the guests reveal about our ability to hold two truths at once. Oumuamua strengthened a healthy minority tradition in science that says our models are servants, not masters, and that when an object leans hard against the wall, we must listen. Borisov reminded an equally healthy tradition that says the universe usually chooses the simplest script that fits the stage, and that oddities should be tested against the ordinary before they are celebrated as absolute novelty. 3i Atlas asks whether we can keep both traditions alive in the same conversation. Can we be open to strangeness without being hungry for it? Can we be comforted by the familiar without letting comfort dull our diligence? These are not philosophical questions thrown in for color. They become daily practicalities when, for instance, a non-gravitational nudge is claimed or denied, or when a spectrum hints at a molecule whose announcement would get clicks. Will we ask for confirmation from independent instruments, or will we let eagerness outrun caution? Will we let a strange light curve be strange for a season, or will we jam it into a template? The three visitors together say that our character as a community is as much the subject of this decade as the objects themselves. There are educational chapters inside each story that we can read without picking sides. Oumuamua teaches cadence. When an object gives you 40 days, you cannot behave as if you had 40 weeks. That means tighter coordination, agreements on what minimum viable coverage looks like, and a willingness to leave some experiments on the table to nail the ones that carry the most weight. Borisov teaches calibration. When you are blessed with a cooperative comet, the best way to honor the opportunity is to be unglamorous in your craft and relentless in your repeatability. 3i Atlas teaches geometry. It shows how much of what we think we know is angle, lighting, and the physics of scattering, and how often we are tempted to mistake a stage effect for a new actor. Holding those chapters together gives us a spine we can use for visitors yet to come. If you want something more concrete than virtues, consider how the trilogy refines our shopping list for future missions. Project concepts that aim to intercept or chase a new interstellar object cannot be built around certainty. They must be built around envelopes, one for how fast and from which angle a visitor might arrive, one for how bright or barren the coma might be, one for how often Earth will have poor seats when the interesting physics unfolds. Oumuamua sets the lower bound on how quickly an arrival can demand attention. Borisov sets the expectation that a basic cometry toolkit will often suffice. 3. Atlas sets the constraint that geometry can blow your plans out of the water unless you design flexibility into how and where a craft can point and what it can do when the sun hogs the stage. Those constraints are not disappointments. They are the information you need before you spend a decade and a fortune on a machine that will have one shot. There is also a cultural lesson that matters beyond labs and domes. In public conversation, Oumuamua continues to serve as a mirror. People bring to it their tolerance for ambiguity and their appetite for extraordinary explanations. The most instructive voices have been the ones that can say both that some data remain odd under simple models and that the burden of proof for extraordinary conclusions is still unmet. Borisov, by contrast, has not stayed in headlines because familiarity rarely does. That is an error in our attention economy, not in the sky. The ordinary case from beyond is as radical a message as the odd case. It tells us that what we have learnt locally is not parochial. It deserves more airtime than it got. 3i Atlas taps both veins of interest because its behavior feels dramatic while its physics remains so far sober. That mix can be a teacher if we let it. It can train audiences to love careful updates and to treat delayed conclusions as a mark of seriousness rather than a lack of nerve. My own view, plainly stated, is that the best posture across the three is to love the puzzle and distrust the rush. I am happy to hold Oumuamua's anomalies at arm's length without needing them to be a message. I am grateful to Borisov for being a bridge between our backyard and the rest of the neighborhood. I am content to meet 3I Atlas as a busy, tilted comet that demands good geometry more than it demands new physics. I would be delighted to be surprised by any of them if careful. Repeated measurements cornered me into a change of mind. The threshold for delight is not a rumor or a single frame. It is a pattern that survives independent attempts to break it. If we ask, what habits should carry from this comparison into the next decade, the answers look practical. Pre-register for our tests. Decide, before the next visitor arrives, which combinations of behavior would count as evidence for unusual dynamics and which would be ordinary given realistic priors. Agree on what kinds of non-gravitational signals deserve extra attention and what minimal suite of follow-ups should be automatic before a strong claim is made. Build small, durable collaborations between large facilities and distributed observers so that cadence and calibration are both covered. Teach more young astronomers that geometry and phase are not footnotes but first steps. Encourage modelers and observers to speak in the same verbs so that predicted signatures can be looked for honestly and null results can be reported without shame. It is also fair to ask what the 3 visitors do to our sense of place. When you first learn that a body from another star has moved through your sky, you feel the neighborhood expand under your feet. The second time, the feeling matures. The third time, it becomes normal. Normal is the right word. We live in a galaxy where small bodies are thrown and traded between systems over long times. We have finally gotten good enough at looking to catch a few in the act. The future holds not a single revelation, but a long series of minor adjustments that, together, will change the way we draw the border between local and not. That is quieter than the big headline many people hope for. It is also truer to the way science usually advances. You barely notice the furniture moving until one day the room feels different, and you do not remember the moment it changed. Side by side, Oumuamua, Borisov, and 3I Atlas do not demand a grand narrative. They invite a better craft. They teach cadence, calibration, and geometry. They challenge our appetite for drama and reward our taste for patience. They give us checklists instead of slogans. If you find that less exciting than the scripts that promise to blow your mind, I understand. But I would argue that the steadier thrill lasts longer, and that it builds a kind of trust between the sky and those who speak for it. When we do finally meet a pattern that resists the ordinary in ways that pre-committed tests cannot absorb, the world will know it because the voices it has learned to trust will say so, and their restraint in earlier seasons will make their excitement contagious. The next question follows naturally and cannot be avoided. Once you have compared what we saw and what we learned, you must decide how to organize your uncertainty. 2 families of explanations sit on the table, as they have since the first sliver raced away from us. One family says that nature can be odd without being intentional, that ice and dust and light are capable of more choreography than our first models allowed. The other family asks whether some signatures might, in the end, be the footprints of design. It is a debate worth having, but only if we set the rules carefully, remember what evidence looks like, and resist the shortcuts that probability and projection invite. That is where we go next, with both eyes open. There are 2 ways to hold a mystery in your hands. One is to turn it slowly until the light reveals the ordinary seams you could not see at first glance. The other is to ask whether the seams do not belong to nature at all, but to craft. With 3 Atlas, the conversation has found both grips. One family of explanation says that ice, dust, sunlight, and vacuum are capable of more choreography than our first models allowed. The other asks whether a small remainder of behavior could, after every natural path is tried and found wanting, be the footprint of design. It is a brave question, but bravery is not the same as haste. If we want to be fair to the sky and fair to ourselves, we must let both families speak under rules that make their claims comparable and their failures instructive. Begin where humility lives, with natural weirdness. Comets are laboratories where sunlight writes on ices in real time. Their surfaces are patchy, their vents irregular, their skins a quilt of fragile crust and fresh exposures. Small torques from gas jets can change rotation periods over weeks. Dust grains of different sizes scatter and glow in ways that make a halo look larger or more vigorous when the geometry is kind. Forward scattering near small sun angles can boost brightness as if a hidden engine had been opened, when the only engine is light and the only valve is angle. Tails disconnect and regrow under the pulse of the solar wind. These are not corner cases. They are everyday physics expressed on a moving stage. When we meet an interstellar visitor, it comes with no guarantee that its surface or mix of volatiles will resemble our local family, and that freedom only widens the range of ordinary outcomes. The result is that behavior we do not expect at first. Blush may still sit comfortably inside the space of natural explanations when we take geometry, activity, rotation, and the vagaries of dust into account. Now set the other lens on the table, the one labeled techno-signature. The word simply means a measurable sign more consistent with technology than with geology or simple chemistry. It does not have to be grand. It does have to be discriminating. To count as a techno-signature, a measurement must prefer an engineered hypothesis over a natural one by a margin large enough to survive honest attempts to rescue nature. It must also come with a chain of reasoning that others can reproduce and attack. A narrowband radio signal fixed to the sky and drifting in frequency exactly as a Doppler model predicts for a moving source is one such sign. A sequence of coherent optical flashes that repeat with an information-bearing structure is another. A sustained, non-gravitational acceleration that cannot be explained by gas jets, by radiation pressure on dust, or by any plausible outgassing model, measured across many nights and instruments, would move the needle. An object whose thermal emission refuses to match any physical surface, unless you allow for waste heat management, would be a candidate. None of these examples is a claim. They are sketches of what a strong case would look like if nature were to yield. Between those two lenses sits a rule that has served us well far beyond astronomy. Extraordinary claims require extraordinary evidence. The sentence only works if we let the words carry weight. Extraordinary does not mean exciting. It means unlikely under a well-specified natural model that has earned its place by explaining many other cases. Evidence does not mean a single frame or a clever argument. It means a pattern that persists across independent instruments, across wavelengths, across nights, and across teams, with uncertainties on the table and failure modes tested in the open. If that sounds austere, it is because our imaginations are generous and our memories forgiving. A community that wants to keep trust must raise the bar higher than enthusiasm can reach. What then would count as natural in the face of a puzzling measurement, and what would push us across the border? Start with motion, because motion is where many of the loudest debates begin. A comet on an open path will follow gravity with great faithfulness unless something pushes. Gas jets can push. The light of the sun can push particles small enough to feel its pressure as a force. The drag of a growing coma can change how light is distributed in our apertures in ways that mimic small shifts in the center. The right test for a true non-gravitational acceleration is not a fit that leaves a small residual on a single instrument. It is a long arc of astrometry measured by multiple teams with multiple cameras that holds its shape under different strategies for subtracting coma and tracking the target. And that continues to prefer a thrust term even after those housekeeping choices are varied. If you can change the answer by changing a photometric aperture or by updating a background model, you do not yet have a force. You have a warning that your measurement is closer to apparent than intrinsic. If, after that gauntlet, a push remains that cannot be matched by any reasonable outgassing model, then it becomes interesting in a new way. Light curves and shapes are another place where the two lenses meet. A small bare body will often show a clean rhythm as it turns. Bright, when a broadside faces us and dim when the narrow edge does. A body surrounded by a coma smears that rhythm into a suggestion. If someone claims a highly regular beat in such circumstances, the next question is plain. Does the beat persist when you change filters and apertures? Does it survive different stacking strategies and varying conditions? Does it repeat across instruments separated by thousands of miles and dozens of dawns? When it does, you are measuring a physical rotation or a commuting vent. When it does not, you are probably measuring your own pipeline. Even a rotation that refuses simple models is not a signature of craft. Nature permits tumbling, precession, and long periods. Technology would have a right to be smoother than rock, not rougher. If you want to argue for design from a light curve, you would need either a level of stability and control we do not see in comets, or a modulation that carries structure no spin should carry. Chemistry feels, to non-specialists, like the most obvious place to find intent, because certain molecules have talismanic power in our culture. The truth is less theatrical and more beautiful. Spectra from a distance tell us that carbon families glow when sunlight pumps them, that water breaks and sings in ways we can recognize, that dust with a certain mix of sizes reddens the light that passes through it. None of these chooses a story. A claim that the coma carries a molecule whose presence would strongly prefer an engineered origin must clear a very high bar. It must survive the overlay of telluric lines from our own air. It must rise above blends with neighbors whose wavelengths crowd in. It must be seen again by a different instrument, on a different night, with a different slant. And it must make sense in the company of other features that would be its friends and enemies in the same band. Even then, chemistry moves slowly from hint to claim. We have learned the hard way that a good upper limit protects more truth than a glamorous assignment that the next season erases. Radio and optical searches for carriers of information are a more straightforward arena, and they come with their own cautions. A narrowband tone that sits like a needle in a broadband haystack is rare in nature and common in engineered transmitters. That makes it tempting to declare victory when a bright one appears. But the sky is cluttered with our own leakage, and with satellites that move in ways that can trick a tired observer into believing the sky itself spoke. The antidote is discipline. Track the tone over hours and watch the Doppler shift match, or refuse the model of a source moving with the comet. Ask a distant station to listen and see if it hears the same song at the same time. Look for harmonics and for modulations that carry structure which a plasma does not. If the tone does not obey the clock and the curve, it belongs to us. If it does and persists, your claim grows teeth. A similar logic applies to fast laser flashes. Coherence, repetition, and a match to the moving frame of the object matter more than drama. It is also worth speaking plainly about geometry, because geometry is where suspicion often makes its camp. A path that hides perihelion from Earth, while giving Mars a better look, later skimming the broad realm of Jupiter, has been treated as a tour by some, and as an ordinary consequence of angles by others. The right way to judge such arrangements is to measure how often they arise under a model that does not know stories. The wrong way is to multiply small numbers you chose after the fact until you feel a chill. If a sequence is rare under fair assumptions, we should say so and ask why. If it is common once you count all the ways the sky can be inconvenient for us and convenient for a camera somewhere else, then the lesson is not about intent. It is about our tendency to treat surprise as meaning. My own discipline here is to refuse to let improbability carry more than it can. A small number in isolation is a mood, not a measurement. Set these cautions beside the possibility that nature may fail us, and ask what standard would satisfy a careful skeptic. A robust techno-signature would show a control or a structure that cannot be coaxed from dust and ice and light, no matter how the deck is shuffled. That could be a maneuver that changes velocity or direction in a way no venting model can mimic, and that coincides with nothing else in the environment. It could be a thermal signature that looks like waste heat from a surface whose brightness and temperature refuse to live on the same physical curve. It could be a signal that carries information dense enough to exclude any known natural oscillator. It could be an object whose reflectivity and mass, measured independently, insist on materials we do not know how to make by accident. The test is not that such ideas can be imagined. The test is that they can be formulated in advance, measured with declared thresholds, and invited to fail. Falsifiability is not a slogan here. It is how we behave when the stakes are high. 3i Atlas gives us a chance to practice this posture in the open. The natural model has a long list of chores it can do with a straight face. It can build an early loud coma from fresh volatiles exposed at a distance. It can boost brightness near small angles with forward scattering. It can alter a rotation period with gentle torques. It can push a centroid around with jets in ways that contaminate naive astrometry. It can cut and heal a tail under the wind from the sun. It can intersect Mars's better angles without sending a postcard. If we want to test beyond that, we must design observations that try to corner the object into showing either a purely natural repertoire or something else. That means precise astrometry before and after glare, with methods and apertures varied on purpose to smoke out adjustments masquerading as force. It means spectra spread across wavelengths, taken at different phase angles, to watch whether a claimed feature behaves like physics or like a processing artifact. It means opportunistic but disciplined radio and optical listening for coherent, drifting signals tied to the object's motion rather than to our own machines. It means committing in writing to what would change our minds, not only to what would confirm our hopes. It is no secret that some voices are comfortable proposing designs sooner than others. The conversation is not a contest between optimists and scolds. It is a rehearsal in how to disagree without throwing away the thread that ties a public to the process. My own view is simple and, I hope, fair. I appreciate colleagues who push hypotheses that stress our models, because stress reveals where a model is brittle or lazy. I also appreciate colleagues who plant flags at the border that say this part of the landscape belongs to known physics until a proper expedition says otherwise. I am happiest when those two kinds of thinkers share a lab bench and a calendar, deciding together which tests are clean and which words are earned. The worst version of the debate is theatrical, with names hurled and motives assigned. The best version is technical and slow, and it ends when a measurement that both sides agreed would count goes one way or the other. There is a quiet, educational habit that helps here, and it belongs to everyone, not just to the people writing proposals. Ask of any dramatic claim whether it has a null model. A null model is a sober outline of what you would expect to see if nothing unusual were happening beyond the mechanics already on the table. If a claimed acceleration vanishes when you change how you subtract the coma, the null model just got stronger. If a claimed spectral feature fades when you correct for air in a slightly different way, the null model wins again. If, after those checks, the claim remains, it graduates to something worth arguing about. The point is not to be cynical. It is to give ordinary explanations every chance to succeed before you write an extraordinary headline. Where does this leave a viewer who simply wants to know whether to be excited? I think the answer is generous. Be excited by the process. Be excited that we can name in advance what kinds of measurements would pull us across the line. Be excited that interstellar visitors now arrive often enough that we can pre-register the tests and wait to see which way the coin falls. If you want a single sentence that captures the spirit I think the sky deserves, it is this: let wonder set the question, and let discipline decide the answer. I can live happily with a natural 3i Atlas that behaves like a lively comet from a different neighborhood, because that outcome still enlarges our map. I can live happily with a surprise that survives the sober checks I have described, because that outcome would enlarge our sense of company. I cannot live happily with a season in which we trade either outcome for a performance. There is a bridge from this careful stance to the tools many people hope will speed our judgment. Artificial intelligence and its cousins tempt us with their taste for patterns and their speed. They also inherit our biases and our blind spots when we train them carelessly. If we are going to ask algorithms to help us separate natural from engineered, We must teach them to respect the null model first, to weight independent confirmations higher than single frames, to flag claims that rely on a single instrument or a single pipeline, and to surface disagreements rather than to smooth them away. That is not a refusal of help. It is a way to ensure that the help we accept makes us slower to claim and quicker to check. The next chapter belongs to that conversation, because our curiosity deserves tools that magnify our best habits, not our worst. So we stand with both lenses in reach, nature first, in all its capacity for surprise within rules we already know. Design as a hypothesis reserved for the remainder that refuses those rules under tests we agreed upon in advance. Between them, a code of conduct that values falsifiability, replication, and plain language about assumptions. It is not as noisy as the versions of this debate that earn the most clicks. It is more durable. If 3i Atlas has something unusual to say, this is the posture that will hear it. If it does not, this is the posture that will let us learn honestly anyway. There is a special kind of temptation that appears whenever a field meets a powerful new tool. The tool makes hard things look easy and slow things look fast. In that first glow, it is natural to imagine that the stubborn parts of the work will melt. Artificial intelligence sits in that glow for astronomy right now. It promises to find needles in sky-sized haystacks, to sort signals from noise without blinking, to fit complicated curves and declare a winner before human arguments finish their coffee. With 3i Atlas on stage and the hours precious, the promise is even more seductive. If a model can tell us what matters and filter what does not, perhaps we can reach stronger conclusions sooner. The promise is real. The limits are real too. Hype and help arrive together. The only way to keep our balance is to name both. Begin with the best reasons to use learning systems in the first place. Modern surveys create torrents of images and spectra too large for any team to read by hand. An interstellar visitor complicates that flood by moving quickly across the sky, changing brightness as geometry shifts, and slipping in and out of ranges that are kind to one wavelength and cruel to another. Classification tasks that once took hours can be learned by a machine that has seen enough examples. A model can flag frames that look like past comet with jets, or spectra that carry a familiar family of carbon emissions, or astrometric fits that misbehave in ways that hint at a processing error rather than a physical push. It can schedule follow-up by predicting which targets are likely to be informative tomorrow morning and which will be spent on. It can fuse records from different instruments and put them into the same frame of reference, allowing a human to see a pattern the way a conductor hears an orchestra instead of a single instrument practicing alone. Those are honest gains. AI can also automate the dull work that good analysis requires. It can enforce the same photometric apertures across hundreds of nights. It can regrid images onto the same coordinate system with the same kernel every time. It can check that calibration stars are steady and report when one of them has betrayed us. It can run the same coma subtraction recipe against raw frames and against frames with artificial tails baked in, so that we know how often our pipeline hallucinates structure or erases it. It can simulate thousands of light curves that differ in rotation period, coma strength, and seeing, then ask which combinations would fool us into claiming a rhythm where none exists. Deployed like that, a model is not a crystal ball. It is a mirror that shows us where our habits are weak and where our confidence is well earned. The gains are largest when the questions are boring in the best sense. Is the guiding stable? Are the comparison stars trustworthy? Does the subtraction of the sky background leave a clean floor? Are the astrometric residuals centered or lopsided? A model trained on healthy data can tell when a new night smells wrong, even when the plot still looks right. It can rescue long campaigns from the one night where a loose cable or a thin cloud would have planted a bias that spreads like dye through every downstream result. When you hear people talk about AI as an assistant rather than a judge, this is what they mean. The assistant protects the craft. The humans remain responsible for the claims. Now the cautions, stated plainly. A model only knows the world it was shown. If you train a system on comets in friendly geometries and then send it to see near the sun's glare, it will see friendly geometries even where they are not. If you feed it a catalogue in which every brightening near small sun angles was labelled as an outburst instead of as forward scattering, it will hand you outbursts on demand. If you pre-select the nights that look interesting and omit the dull ones, the model will learn your appetite instead of the sky. That is how bias travels from our hopes into the machine and returns dressed as authority. The antidote is not to walk away from AI. It is to treat training data the way you would treat a scientific instrument. You calibrate it, you stress it, you ask what it ignores, you tell the world what you fed it and why. Overfitting is the name we give to a model that memorizes quirks instead of learning patterns. In astronomy, those quirks hide everywhere. A single telescope's optics leave a fingerprint on stars near the edge of a field. A particular night's atmosphere leaves a grain in the noise that repeats in small ways across frames. A readout amplifier draws faint stripes that a human will not notice unless prompted. A model can learn those marks by accident and then declare a comet's coma to be streaked when the streaks are only in the camera. The only reliable defense is to evaluate on data the model has never seen, from instruments it was not trained on, with processing steps it did not learn. Cross-survey validation is not a luxury. It is the difference between an assistant and a parrot. Explainability matters too. Some models behave like black boxes, producing a label without showing their work. For problems where the stakes are low, that can be tolerable. For questions that will reshape a community's narrative about a rare visitor, it is not. If a model says a spectrum contains a feature of interest, it must also show the region that drove the decision, quantify how the call changes when the baseline shifts, and report which training examples it thinks this case resembles. If it flags a non-gravitational signal in the path, it must be able to show how choices in coma subtraction or aperture size change its confidence. Humans may still disagree about the thresholds, but at least they will disagree about visible steps rather than about magic. There is also a danger in treating a single output as proof. The most meaningful product of a learning system in this kind of work is often not a yes or a no, but a ranked list of candidates and a measure of uncertainty attached to each one. If the model surfaces the 10 sessions most likely to contain a repeating jet structure, the job for humans is to test those sessions with independent methods. If the model says these 20 spectra most resemble dust-dominated comet, and these 5 look gas-rich, the job is to observe the next morning with a different instrument that can arbitrate. Far from replacing the slow work of confirmation, AI can make that work more efficient by pointing to where our time would be best spent. Used this way, a model is a triage nurse, not a surgeon. Consider the special case that makes people lean forward. Could a model find a techno-signature faster than a person? It could flag unusual patterns that are easy to miss, yes. It could notice a narrowband tone drifting in precisely the way a moving source would impose, hidden under a forest of terrestrial noise. It could find coherent flashes in optical records that were archived and forgotten. It could suggest that a sequence of small accelerations read like a plan instead of like messy venting. But every one of those suggestions still needs to pass the same gauntlet of falsifiability as if a human had had the idea. A model can help write the hypothesis. It cannot award the trophy. If anything, the bar should be higher for claims that originate in a learning system because the space of ways to fool oneself grows with complexity. The discipline must grow to match. There is a quieter gift that AI can offer our community if we let it. It can help us pre-register our curiosity. Before the next interstellar visitor arrives, we can teach a system to simulate realistic astronomical scenes with and without the features we care about. We can bake in coma patterns, rotation speeds, seeing conditions, instrument quirks, and solar wind weather. We can then ask the model to write down which test would be most powerful at telling the natural from the unusual. It can tell us that, given the timing and the path, a month of short exposures will recover a light curve more often than a week of long ones. It can tell us that a particular ultraviolet line would settle a chemistry question faster than another, given the phase angles we expect. It can help us allocate precious telescope time where the bad cases are less likely to fool us. That is not flashy. It is the kind of homework that turns a sprint into a plan. People sometimes ask whether AI can finally solve the argument between story and skepticism. It cannot. It can sharpen it. A model can estimate how often a sequence of angles like the one 3i Atlas carries would produce poor views from Earth and better ones from Mars, purely under geometry. It can sample that world honestly and say whether our sense of surprise has a denominator. It can expose the hidden dependence between events we were tempted to multiply as if they were separate. It can warn when a tiny probability was manufactured by painting a target around the arrow after it hits the board. But a model cannot tell us how much proof we require before we accept an extraordinary claim. That threshold is a human agreement born of history and temperament and the value we place on being slow or being bold. AI can make our math cleaner. It cannot pick up our courage for us. There are operational details that decide whether AI helps or hurts on a given night. Time stamps matter. A model trained on light curves will punish sloppy clocks by finding rhythms that are only errors. Downstream checks matter. If one instrument's images pass through a sharpening filter and another's do not, a model will split them into tribes for the wrong reasons. Data sharing etiquette matters. Learning systems that thrive on large, diverse samples cannot do their work if the samples are kept in private drawers until the season has passed. It is not romantic to talk about file formats, metadata, and pre-agreed pipelines. It is how powerful tools keep their power without making our arguments more confusing. My own opinion, clear and simple, is that AI belongs at the beginning and the middle of our work, not at the end. It should propose candidates, surface anomalies, standardize housekeeping, and simulate the worlds in which we will test our ideas. It should not be asked to pronounce. When it seems to pronounce, we should treat its confidence with suspicion until a measurement we would trust from a human confirms it. I do not want a model to replace my uncertainty. I want it to make my uncertainty better aimed. When an outcome depends on a choice of priors, I want the model to say so and to show how changing those priors changes the answer. When a label depends on a narrow band of the spectrum, I want the model to say that too, and to suggest a second band where nature would agree or refuse. Humility can be coded. It should be. There is also a cultural task that will decide whether AI becomes part of our discipline or another source of noise. We need a norm that says models used in claims about rare visitors must be accompanied by notebooks that can be run by other teams. We need a norm that says training sets must be described, with their biases and holes noted plainly. We need a norm that says negative results are worthy of print when they close doors that hype had opened, and the upper limits are our first-class citizens, even when a model would rather hand us a bright label. The craft we are trying to protect is more than numbers. It is a way of talking to each other that keeps trust alive when the sky is stingy and excitement is high. For observers following from home, there is a simple way to listen for whether AI is being used well in any claim you hear about 3i Atlas. Notice whether the voice making the claim describes the training data. Notice whether they say what would have changed the result. Notice whether another team repeated the analysis on raw data and obtained the same answer without the same code. Notice whether the call from the model led to a fresh observation that confirmed or denied it. These are not technical hurdles laid to keep newcomers out. They are the steps by which excitement becomes knowledge. When you hear them, relax. When you do not, keep your hands on your wallet. The happiest role for AI in this story is to help us be more patient in the right places and less patient in the wrong ones. It can teach us when a brightness surge is most likely to be a lighting trick by showing us how often similar surges have arisen in synthetic comets under the same angle. It can teach us which spectral windows will pay us back fastest when dawn sessions are short. It can keep our cadence honest by flagging nights when we fall out of rhythm. It can pay special attention to windows near Mars and near the Sun, where our eyes would otherwise be tired and miss a detail. In the weeks when glare made Earth a poor witness, a model can make sure the trickle of possible frames from other vantage points is sifted and shared with care before the window closes. If, after all of this, you are hoping that a machine will hand us a verdict on design or nature for 3i Atlas, I cannot give you that. I can give you a better promise. If we use AI as a partner in preparation, if we keep it near the measurements and far from the headlines, if we insist on transparency and replication, then whatever conclusion we reach will be sturdier. We will not arrive faster than the truth. We will arrive as fast as truth allows. There is a difference, and it matters. Tools are only as noble as the work we ask them to do. The sky has never rewarded shortcuts. It rewards checklists, patience, and courage, when courage is finally earned. AI can write the checklist with us. It can remind us to be patient. It can warn us when our courage is really just hunger wearing a lab coat. Used that way, it will have a hand in every careful graph we draw in the months after the sun steps aside and the traveler comes back into gentle light. Beyond algorithms and archives, there is another way to close the distance between curiosity and proof. If we want answers not filtered through glare and chance, we can shorten the story. We can meet future visitors farther from the sun, sooner after discovery, and with instruments built to touch the problem directly. That is the dream behind concepts that chase or intercept the next messenger from elsewhere. It is not enough to be clever with data. Sometimes we must go. If patience is our sharpest instrument from the ground, preparation is our sharpest instrument in space. 3i Atlas reminds us that geometry can turn the best week into the worst seat, that glare can mute the moment when physics sings loudest, and that interstellar guests do not slow down to fit our calendars. The cleanest answer is not a better caption after the fact. It is a better posture before the fact. Send something that can move. Park it where the angles are kind. Give it the eyes and the judgment to sprint when a new object crosses the threshold from rumor to reality. We call such a craft an interceptor, and the next decade may be defined as much by how seriously we take that word as by any single comet we chase. An interceptor's creed is simple. Do not wait for the perfect target. Be ready for the next target. That means living in a place where the sky opens wide, not locked to one planet's dawns and dusks. It means carrying enough agility to pivot toward a visitor whose details you will not know until hours or days after discovery. It means narrowing ambition to the instruments that matter most and building the rest of the mission around getting those instruments in front of the object fast, steady, and safe. From a distance, that sounds like attitude. Up close, it is engineering. Where would you keep such a craft? Space has neighborhoods that are friendlier to watchers than others. One is a gravitational lullaby called a Lagrange point, where the pulls of the sun and earth balance in a way that lets a spacecraft loiter with modest effort. From such a perch, an interceptor can see a large swath of sky without fighting atmospheric glare or day-night cycles. When a new interstellar object is announced and its path sharpens into a corridor rather than a fog, a craft at the right Lagrange point can drop the waiting pose and begin to lean. The early hours are not for heroics. They are for reshaping the trajectory so that, weeks or months later, a close sideways pass becomes possible at speed. The closer that pivot begins to the discovery moment, the larger the set of targets that remain reachable. What would you put on the board, not the kitchen sink? A long campaign with 3i Atlas teaches restraint. You want a camera that can handle both the glare of a bright coma and the faint texture of a dust tail, with exposure control that does not blink when particles streak past. You want a spectrometer that can read the bright, broad bands that speak of dust and ices, and the narrower features that sing when sunlight pumps simple carbon families. You want a way to measure the size and direction of dust grains, which might be as humble as polarization sensitivity, or as direct as a tiny sensor that counts impacts as particles tap the hull. You want a thermometer for the coma made of light in the infrared, where warm dust and certain ices glow, and you want all of this to work in a choreography that does not demand a pilot's hand on every dial. A target that rushes past at tens of kilometers per second will not wait while you reconfigure menus. Propulsion is not just how you go, it is how you think. Chemical engines are the sprinters. They give you muscle for short pushes, perfect for a craft that must sit quietly for months and then act decisively when the window opens. Electric propulsion, the slow and thrifty ion engines that sip propellant while pushing for weeks, are the endurance runners. They are powerful when used early and cleverly, shaping a path while the target is still distant. Solar sailing is a poet's answer that sometimes becomes an engineer's. Light itself nudges a large, thin sail. Done well, that nudge adds up, changing the plane of a craft's orbit without a drop of fuel. Each option shapes the set of visitors you can meet. An honest interceptor will accept limits and declare them in advance. Pretending you can be all things to all targets is a way to be late for every target. Navigation is the quiet genius of such a mission. On the ground, an orbit is a list of positions on the sky, with times beside them. In flight, an orbit is a guess you constantly improve. An interceptor has to recognize its target against a busy star field, often in cramped lighting, and steer without twitching. That means optical navigation that notices the way the comet slides against background stars and turns that noticing into a steady hand. It means an exact clock, because a light curve you build on board must line up later with the ground truth. It means cameras that can swap roles, pointing wide for context and then narrow for detail, without losing the target during the switch. Many missions know these arts. An interceptor must know them at speed while crossing a river of dust. An educational note belongs here, and it is simple enough to carry in a pocket. When we talk about the difficulty of catching an interstellar visitor, we are really talking about two old friends in orbital mechanics: energy and plane. Energy is how hard the throw is. The plane is which sheet of paper in a stack that the orbit draws its oval. Changing energy is easy to imagine. Changing planes is surprisingly expensive for rockets, especially when you wait too long. A pre-positioned interceptor buys both, cheaply, by starting early. A small sideways push far from the encounter does the work of a large sideways push near it. That is why waiting in a good perch matters. It creates time you cannot buy later. There is also the question of what to risk. An intercept at high speed is a close conversation with a fog of dust. Tiny grains become bullets. Spacecraft survive micrometeoroids all the time, but a deliberate pass through an active coma asks more. Shields add mass. Mass adds cost. Cost takes away agility and sometimes the mission itself. The honest compromise is to dip sideways rather than straight in, to favor an approach that sees the structure of the coma and tail in parallax without plowing through the thickest part. What you lose in bravado, you gain in longevity and in the chance to make more than one pass through the outskirts as geometry evolves. A craft that lives to intercept twice turns one miracle into a program. Data is where dreams get small and real. An encounter at speed produces more images than you can send home right away. The link back to Earth is finite. The Deep Space Network, or its cousins, are busy with other commitments, so the craft must learn to triage. That means onboard processing that picks the sharpest frames when jitter sneaks in, that compresses wisely without killing the features Spectra need, that recognizes when a sequence has redundancy and can be sampled instead of slavishly transmitted frame by frame. It also means a ground team willing to embrace imperfection. You will not get everything. You will get enough if you decide ahead of time what enough looks like. Suppose someone says, "Why chase at all? Why not build a telescope so large and so clever that it makes every interceptor unnecessary?" The answer is that remote sensing and close sensing are different instruments in the same orchestra. A spectrum taken from Earth teaches you about the chemistry of the lightest gases and the finest grains. A camera that skims the edge of a coma teaches you about texture in a way that can never be recovered from a faraway smear. A polarization map read from a few thousand kilometers tells you how grains align and scatter that would be hidden by distance. A dust counter that clicks as particles pass does not need a model to explain its units. The two approaches strengthen each other. The best strategy is not either or, it is both now. A second educational note is worth saying aloud because it helps decision makers. The most valuable minutes of an intercept are not necessarily the minutes closest to the nucleus. They are the minutes when the geometry lets you measure something you cannot measure from Earth. That might be the way jets braid into the inner coma. It might be the way the color changes across the bright center where ground-based telescopes saturate. It might be a parallax that pinches the knot in a tail kink and gives its true distance instead of a projection. If you design the mission around that sentence, you build a better instrument. If you design around the dream of a postcard, you build a fragile one. People sometimes point to the sprint we missed for Oumuamua and ask whether it is even possible to catch a fast scout without a miracle. It is hard, but the lesson from that year is not that we were doomed. It is that we were unready. We did not have a craft with the right fuel and the right instruments, and a guidance system trained for that task. Since then, mission concepts have explored ways to stack speed, use the biggest upper stage you can borrow from a rocket's last breath. Borrow momentum from a planet with a gravity assist that slings you into a new plane. Consider a sail large enough to lift you slowly out of the ecliptic, where you can see arrivals from above rather than always from the side. Each idea has trade-offs. Some demand hardware we have, some demand patience, we do not. The point is that the barrier is not physics. It will. What then would a modest, credible interceptor program look like if we were to begin tomorrow? It would start with a single craft, stationed where the sun and earth make loitering cheap. It would carry a compact camera that can switch between wide and narrow fields and hold focus in a dusty environment. It would carry a modest spectrometer in the optical or ultraviolet that can survive a bright coma and still measure faint lines. It would carry a simple infrared eye for dust warmth. Its antennas would be sized for honesty about downlink, and its computers would be trained on the ground with synthetic comets that teach it which frames to save when the seconds blur. Its propulsion would be enough to change plans slowly, and then, near encounter, to tap the brakes just enough to keep the target in view during the minutes that matter. Most importantly, its team would include people who live on call. Discovery will not respect office hours. My opinion, plainly offered, is that we should also invest in the boring parts that make the exciting parts real. That means better, faster pipelines that turn survey detections into orbits with honest errors in hours, not days. It means agreements between observatories that reserve a thin slice of time for target of opportunity work, without rancor, so that the first nights after discovery are not spent begging for a slot. It means teaching young scientists to think like dispatchers, as well as like analysts, because the window an interceptor needs often opens or closes, based on a decision made while the coffee is still warm. Behind every glorious close pass is a spreadsheet with good phone numbers and a culture that treats go and no as sentences made of reasons, not of hope. It is fair to ask whether 3i Atlas itself could have been intercepted if we had started years ago. The honest answer is that you design for a family of possibilities, not for a single comet in hindsight. Atlas's geometry, with its glare and its gifts to Mars, is a teacher either way. It shows us why a perched craft, with the patience to wait, would be a different kind of witness than a world bound to one horizon. It shows us that the scientific value of a fast pass does not live only in a hero image. It lives in confirming the size of the nucleus under a thinning coma, in watching jets stitch the inner glow into a pattern you can follow, in reading the true twist of a tail under a wind you can measure in situ rather than infer from afar. Even a miss teaches. An interceptor that spins to look and cannot quite get there still sends home a map of how to do better next time. You may be wondering where the public belongs in something that sounds so technical. The answer is not at the edge, it is in the plan. Survey data that finds the next visitor pours through public archives that citizen scientists have helped read for years. Networks of small telescopes many owned by schools and clubs, can test cadence and light curve strategies before a mission ever launches. Amateur spectroscopists can map the bright bands that matter most, teaching an interceptor team which windows pay back the quickest. Even the dry art of timing benefits from volunteers who keep clocks honest in neighborhood observatories, because a light curve that moves between hands without losing its rhythm is as good as another instrument. The most resilient intercept program grows from a community that already knows how to share. There is one more honest limit to name before we step toward the final chapters. An interceptor is not a magic eraser for uncertainty. It is a way to move the front row closer to the stage for a little while. The craft will still read light through dust. It will still fight motion blur. It will still be surprised by a vent that wakes or sleeps at the wrong moment. The victory is not in banishing ambiguity. It is in changing which ambiguities we live with. After an intercept, the arguments we have are better ones. They are about texture, not silhouettes. They are about chemistry in place, not colors from afar. They are about motion in depth, not guesses at a flat picture. That is enough to justify the effort. So the plan writes itself in quiet lines. Park a patient sprinter where the sky is wide. Teach it to see and to triage. Give it the humility to measure what matters most and to leave some dreams unchased. Build a culture on the ground that decides quickly and shares cleanly. Use each close pass to prune the next mission into a sharper tool. And while we practice in space, keep the home team in rhythm so that when the craft hands off the baton, the receivers already know the tune. The last turn in our story belongs to everyone with a pair of eyes and an appetite for the honest kind of wonder. Space is not only a place where agencies act. It is a place where citizens keep the beat, where small instruments fill in the rests between the brass, where careful logs and steady hands make 1,000 quiet contributions that add up to a song. 3 Atlas has given us plenty to do on both sides of the atmosphere. In the next part, we will talk about how people far from launch pads can still shape what we learn, and how a culture of open, careful observing turns a rare visitor into a shared education. A rare object always tempts us to become spectators. The better choice is to become witnesses. Spectators ask for a show. Witnesses keep a record. With 3 Icy Atlas, the weeks when glare loosens and dawn returns are exactly the time when careful witnesses make the difference between a memorable story and a durable result. You do not need a mountain or $1 million mirror. You need a plan, a steady hand, and the humility to do the simple things well. The sky will meet you halfway. Begin with safety and light. In the weeks bracketing perihelion, the object rides uncomfortably close to the sun from Earth's point of view. Never look at or near the sun without certified solar protection. If you observe in twilight, keep a strict horizon rule. Point only after the sun is fully below the horizon and your line of sight is well away from it. If you try morning sessions, set alarms that remind you to stop before the sun rises. Curiosity is no match for retinal tissue. Write those rules down the way climbers write knots. Your eyes are part of the instrument. Next, set your role. There are many ways to help, and each favors a different temperament. If your joy lives in precision, become a timekeeper, astrometry, and basic photometry that feed the orbit and the light curve. If you enjoy pattern and color, become a chemist from afar. Repeated color measurements with simple filters that track whether dust or gas dominates. If you like rhythm, become a drummer. Light curves taken at the same time each morning, even when the numbers seem dull. If you love pictures, become a cartographer. Wide fields that track the tail's position angle and its changes over days. The worst way to help is to chase everything. Choose a lane and let the calendar teach you. A modest kit is enough. Binoculars on a tripod can follow the broad shape of the tail and the timing of a brightening. A small refractor on a sturdy mount, paired with a DSLR or a cooled camera, can measure brightness and color. A medium instrument can add a low-resolution spectrograph and turn the glow into hums and spikes. Phones can record surprisingly useful wide fields if you mount them solidly and repeat the same settings each session. The best accessory is boring, a notebook. Write down the date and time in universal time, the location, the instrument, the exposure settings, the filters, the sky conditions, and anything that went wrong. I promise you this. The page where you confess a cable glitch will save you from fooling yourself later. Consistency is the quiet superpower. Use the same equipment, same settings, same apertures, and same workflow on each session. If you must change something, different lens, different gain, different focus method, note it clearly and treat that night as a different series when you compare. The goal is not a gallery of your best frames. The goal is a sequence you can stack into a curve without pretending apples are oranges. When you choose comparison stars for photometry, pick ones near the target in the sky and near it in color. Keep the same stars through the whole run. If clouds or haze move through, be honest and stop. A gap is kinder to the truth than a fudge. Calibration sounds fussy until you see what it buys you. Take a few bias frames at your camera's shortest exposure with the lens capped. Take dark frames at the same temperature and exposure length as your light frames with the cap on. Take flats that even out dust and vignetting bright screen, t-shirt method or twilight sky, as you prefer, but keep their exposure in the middle of your camera's range where it behaves best. You do not need graduate school to do this. You need to repeat it. Those extra minutes turn a pretty image into a measurement a stranger can trust. Cadence beats drama. A single spectacular frame will travel far online, but 10 modest sequences taken on 10 consecutive mornings will carry more weight when teams try to nail rotation or separate geometry from physics. Imagine you are passing a baton across longitudes. Choose a short window you can own, say 40 minutes before dawn, 3 days in a row, and keep it even if the first 2 mornings look bland. Somewhere west or east, another person is holding the next leg. Your steady hand turns the pair into a continuous record that a large observatory cannot assemble by itself. If you aim to help with astrometry measuring position to feed orbit refinements, the recipe is simple and strict. Track the stars, not the comet, for short exposures that keep the stars round. Stack along the comet's predicted motion to raise its signal without bending the sky. Use a plate-solving tool to translate pixels into sky coordinates. Check the residuals. If your stars fit poorly, fix that before you measure the comet. Do not round numbers to look neat. Do not guess when the signal is low. If the centroid jumps when you change the aperture by a couple of pixels, mark the night as uncertain. Honest astrometry is a gift. Overconfident astrometry is a poison. If you want to contribute photometry measuring brightness over time, commit to your aperture and your comparison stars. Keep the same annulus for the local sky background. Record the phase angle and the elongation from the sun. They will matter later when teams correct for intrinsic. If you have 2 or 3 simple filters, say clear, red, and blue, cycle them in the same order each morning and note the times carefully. A small color change can signal a shift from dust to gas dominance near the nucleus. It takes only a few seconds to write that note, and months to recover it if you do not. Spectroscopy at home is more approachable than many imagine. A clip-on grating in front of a camera lens or telescope can spread the light into a little rainbow. Keep your expectations humble. You will not map a complex molecule from a backyard. You can record the broad color trend of dust and, under friendly skies, when the comet is bright, hints of familiar gas families. The discipline here is in subtraction. The sky glows with its own lines. Subtract them carefully. If your instrument imprints a tilt or a ripple on every spectrum, measure that on a bright star and remove it before you call a feature real. When in doubt, show your raw and your processed frames side by side. People who know the craft will help you read them honestly. Polarization, the way light's orientation is twisted by scattering, is a subtle but powerful citizen measurement. Even a simple linear polarizing filter, rotated in front of the camera, can reveal whether dust grains near the nucleus are favoring a direction. The amount and angle of polarization change with phase. Record both if you can, along with the angle of your filter. This is an area where amateurs have surprised professionals before. Write your steps down so someone else can repeat them. Wide field workers, your job is to watch the tail breathe. A stable tripod and a lens in the 50 to 135 millimeter range can catch the integrated shape of the dust tail, and with luck, a thinner ion tail that kinks and disconnects when the solar wind changes mood. Compose with bright stars to anchor your field. Keep the same frame night after night. If you see a curl or a spike, note the time and take a short sequence rather than a single long exposure. Tail dynamics love cadence. Your images, aligned and blinked in sequence, can time a cut and match it to reports from spacecraft that watch the sun's wind. A clean timing beats a dramatic still. Where should you send what you measure? Positions to the clearinghouses that feed orbit refinements. Photometry to comet and variable star organizations that accept calibrated magnitudes with metadata. Spectra and wide field time series to the communities that maintain archives for comet observations. If you do not know where to start, ask a local club. They will know the familiar pathways. If a school is involved, treat sharing as part of the lesson. Students learn a deeper science when their numbers leave the classroom and they meet strangers. For classrooms and clubs, 3i Atlas is a semester wrapped in a single object. Build a light curve and teach uncertainty. Plot the tail position angle and see whether it drifts with time. Measure the color index over several mornings and discuss what dust and gas do under changing angles. Challenge students to write down, before they begin, what would count as a real change and what would only look like one. That is how you teach pre-registration without the jargon. Let them predict and be wrong softly, then write more slowly. Science, as practiced, is slower than the shows we grew up on. That slowness is part of its beauty. If you share images online, be a good ancestor. Post your raw alongside your processed frame. State your settings, time, and location. If you annotate, do it sparingly and honestly. Label a suspected feature as suspected until someone else finds it with a different instrument. If your curve has error bars, show them. People will learn from your tone as much as from your numbers. The culture you model now will be the culture inherited by people who meet the fourth interstellar visitor a few years from now. Be careful with language that leaps. Words like proof and impossible quickly cheapen in public threads. Replace them with measured phrases that leave room for the next night, consistent with, so far, under these conditions. Those words are strong. They carry both curiosity and restraint. They also signal to working teams that you understand the contract we try to keep with the world. Excitement up front, evidence underneath. Light pollution advocacy, usually a quiet crusade, belongs in this story too. A diffuse coma and a faint tail drown quickly under the wrong lamp. If you have a voice in a city council or a homeowners association, point their attention to shielded fixtures and warmer color temperatures. In one neighborhood after another, that small change makes dawn friendlier for everyone, not just for people with telescopes. Invite a neighbor to look through yours after you have taken your frames. Curiosity travels better across fences when you share the eyepiece. For those who love software, the sky needs you as much as it needs glass. Write small tools that make calibration easier for beginners. Build scripts that stamp images with the essential metadata in a consistent way. Share templates for observing logs that ask the right questions. What was the air mass? What was the elongation? Which comparison stars? What did the wind do? The dullest parts of the craft are the ones most improved by code, and the tools you write for this object will live long beyond it. If you have only your eyes and time, you still belong. Keep an observing diary of naked eye or binocular impressions taken from the same place at the same time on successive mornings. Describe the tail's length against known stars. Note whether the head was visible or lost in haze. A century of comet records proves that honest impressions, repeated and anchored by simple comparisons, survive fashion and remain useful. The skill you practice is not drawing, it is consistency. The reward is a voice in the record that does not require anything plugged into a wall, a word about claims. When someone posts a bold, one fragment detected, motion changed, exotic molecule seen, ask them for the plain steps. What instrument? What time? What comparison? What changes when the aperture moves or the baseline shifts? What second team saw the same thing? You are not picking a fight. You are defending the idea that good stories are built on parts that can be checked. In the absence of those answers, the safest stance is to wait. Waiting is not a failure in a fast news cycle. It is the sign that you remember what truth costs. There is joy in the ordinary nights that get you nothing special. You learn your mount's quirks. You teach your hands to focus in the dark. You discover which cables sulk in the cold. You memorize the sound of dawn. Those hours are not wasted. They are the apprenticeship by which a witness becomes part of the instrument. If 3i Atlas gives you one morning when the curve bends cleanly or the tail kinks in a way you can time, you will hear the click of all that practice paying off. My own view is simple enough to fit on the same page as your log. 10 honest measurements taken with the same setup over 10 dawns are worth more than one astonishing image. A careful upper limit. Nothing seen brighter than this under these conditions can be as beautiful as a detection. A clear description of what would change your mind is a bigger gift than a confident paragraph. The culture we build around this object will shape how we meet the next, and the next. When you step outside in the dark, you join a chain that runs from observatories to backyards and back again. The chain is strongest where the links are plain, open data, clear notes, gentle language about uncertainty, patience with repetition, kindness when a beginner asks a question you asked once too. If you keep those habits, your town becomes part of the experiment, whether it owns a telescope or not. Soon, this chapter will narrow into a quieter lane, observing seasons pass, tail kinks smooth, comet thin. The visitor will dim in a sky that turns toward other tasks. What remains, if we have done this well, is more than a scrapbook. It is a record with corners square enough to build on. The last thing to say before our story closes is not about equipment or windows or even 3i Atlas. It is about the posture that makes all of this worth doing. A way of seeing that keeps wonder bright and skepticism warm, that treats data as a form of respect, and that knows how to sit with not yet without turning it into never. That posture is the quiet heart of this series, and it belongs in one last room of its own. In the quiet after the glare, the story of 3i Atlas resolves into something steadier than drama. A traveller came through, wrote light into dust, tangled a tale in the wind, and reminded us that geometry can be as powerful as mystery. We answered with patience. We learned to separate candle from window, apparent from intrinsic, bright flourish from the work of small grains at the right angle. We practice the discipline of letting evidence arrive in its own time. If the visitor is only a lively comet from another neighborhood, that truth is generous. If one day it asks harder questions, our best answer will still be the same craft we used here. Curiosity and skepticism are not rivals. They are the two eyes that give depth to what we see. One invites us outside before dawn. The other keeps our notes square and our language careful. Together, they turn a passing glow into a record we can trust. That, more than any headline, is how we learn. Keep the simple promises. Measure cleanly. Share plainly. Treat limits as gifts, not disappointments. Remember that wonder is not fragile. It does not need embellishment. It needs attention. If this journey helped you see the sky with steadier hands and a softer voice, stay with us. Subscribe. Turn on notifications and pass this along to someone who would stand in the cold for a better look. Then step outside and look up. The next question is already on its way.